Just a second. Let me start with the streaming and with the recording. Okay. Okay.
Okay, yeah, welcome back everyone to our second day of our school. We are happy to have a second lecture by Tijna Bhalkar about mock modularity in physics.
Okay, are there any questions? Or okay, let me just start and then maybe we can take a stop for questions from last time. I think the tutorial, we answered most of the questions. So last time we covered, we explained what are modular forms, what are mock modular forms, we introduced various definitions. And then we were asking, in what physical context do we need these what apparently looks like an exotic mathematics? And one was the puzzle with black holes, that in some cases, the counting function is has a pole in one of the variables, one of the fugacities, and therefore it looks like, or one of the chemical potentials, and therefore it looks like the answer would depend on where you are in that pole. Then the second puzzle was with instantons, that what is known as the Wafa-Witten partition function, which is some topological sector of Yang-Mills theory, say on some 4 manifold. Formal argument would suggest that the partition function should be holomorphic, but actually there is no such holomorphic object consistent with S duality. So either you have to give up S duality, which is a subgroup of SL to Z symmetry, or you have to give up holomorphy. And the third was with elliptic genus. Once again, elliptic genus, because it's some partition function, some indexed partition function defined on a torus, a 2 torus world sheet. It should have SL to Z invariance, but once again, the elliptic genus is expected to be holomorphic, but there is no holomorphic object which has the SL to Z symmetry properties. And you need to add some non-holomorphic terms to, otherwise your expectations from conformal invariance are not borne out. So either there is something wrong with conformal invariance, there is something wrong with duality, and there is something wrong with the black hole counting formula, or there is something wrong with holomorphy. And as we will see, from a physical point of view, holomorphy is the thing that we are willing to give up, because these are some duality symmetries are something, more sacrosanct than holomorphy. And in all these cases, the answer actually involves mock modularity from a mathematical point of view. And even though we understood the mathematics, for example, for the black hole problem, we understood it with this paper with Murthy and Zagier in 2012, the physical origin of that mock modularity was not clear. And the past few years, it has become more and more clear. I mean, we had some ideas about where the mock modularity is coming into that problem, but to really derive it from some physical principles like a path integral is what we would like to do. And that's what I would like to describe in this talk. And then Pavel will focus more on the derivation of this mock modularity from a path integral point of view in the context of S duality. So he'll spend 2 full lectures on that. So I will only briefly mention that particular case. Okay, so just to remind you, the resolution of this puzzle that the black hole degeneracies seem to depend on the contour, what seemed like a problem, actually, there was yet another problem that normally the moduli space of the theory should be split up into chambers separated by walls. And in fact, the degeneracies could in principle jump. And so sort of these 2 problems in a way solve each other if you identify the poles in the counting function with walls in the moduli space. So remember, poles are happening in some Z variable. They should not be confused. The poles are in some Z variable of the counting function, whereas the walls or in some moduli space. So it's in the Z plane and this is in the moduli space. But you can actually make a very precise correspondence between the contour in the Z plane. You can make it depend on the moduli in a very precise way in these particular examples. That map has been very well understood. And then as you vary the contour, as you move around in the moduli space, as you vary mu, you vary C. And whenever mu approaches a wall, the contour hits a pole. But that raised another puzzle. How come the quantum degeneracy of a black hole, which should be a property of its horizons, it's some fundamental property of quantum gravity, how can it depend on the asymptotic moduli? Because black hole is somewhere in the middle of space-time, and the asymptotic moduli are far away. Why should the degeneracy of the black hole care about asymptotic moduli at infinity? And the resolution was that actually, if you look at the precise degeneracies of the black hole itself of the horizon, they are in fact independent of the moduli. But depending on the moduli, you may or may not have multicentered black holes. And as you cross the walls, the multicentered black holes can disappear from your spectrum. And then the degeneracy jumps, not because the horizon degrees of freedom jump, but because what were bound states on one side cease to be bound states on the other side. So there is no contradiction with expectations from quantum gravity. And this is nicely summarized. This physical picture actually, in fact, was one of the motivations for this mathematical decomposition theorem. So this is the asymptotic counting function. It counts all states. The partition function which counts all state at infinity receives two contributions, one which we call psi m polar and one which we call psi m finite. The polar part basically counts multicentered black holes, and the finite part counts the single-centered black holes. And these counts all black holes. So basically, when you are in some space-time, you are here far away, and inside the space-time there can be a multicentered black hole, or multicentered black hole or single-centered black hole. So observer sitting far away, the counting function will include contributions from both of them. And the contribution in this particular problem of the type 2 on K3 cross T2, this problem is very well understood. And the contribution of multicentered black holes actually correspond to a very nice mathematical object, which is called the upper-Lurk sum. And the idea of the upper-Lurk sum is the following, that if you look at our counting function, the counting function had a pole, a double pole. Yeah, so as I explained, the polar part counts the multicentered black holes, and the finite part counts the single-centered black holes. And if you remember, your psi m had a theta function tau z in its denominator, and theta 1 square, or and this goes as 1 upon z square times this p24 n plus 1 divided by eta to the 24 tau. Okay, you had some other factors here. So if you look at the behavior of your counting function, the full counting function, at z is equal to 0, it looks like this. And that suggests that you can remove this factor. This factor is we remove it. If you remove that factor and then take some kind of an average, because you have a pole at z is equal to 0, but you have a lattice of points in the complex plane. And so in fact, you have an infinite number of double poles in the complex plane. And therefore, you can create a function which has exactly the same poles as your original function. The original function had poles and it also had the elliptic properties. So you construct an object which is called the upper-Lurk sum, which was done by Appel-Lurk for their own mathematical reasons. But it comes out very naturally in this physical context that you create a function which has the same elliptic properties as your original function and exactly the same poles. After you multiply by this extra factor, and therefore, if you subtract that function from your original function, what is left over will have no poles anymore. And therefore, the Fourier contours for that particular function will be well defined. And that's the function we call psi m f. And again, for psi m f, we can take out this overall factor, and you are left with this object. And the claim is that psi m f was an neuromorphic Jacobi form of index 2 and weight minus 10. So index was m was 2 and weight was minus 10. But if you remember, this eta to the 24 coming in the denominator has weight minus 12. So what is left here? Sorry, I'm saying it wrong. Psi, what am I saying? It had index m depending on what is your m. Okay, I'm not specifying to m equal to 2. So it had index m and weight 10 minus 10. But if you remove this eta to the 24, what is left behind would have in the same index m, but weight 2. And so the claim is that, the claim of this decomposition theorem is that this object, the resulting object, is a mock Jacobi form of weight 2 index m, and therefore, and by definition, a mock Jacobi form is one which does not have nice modular properties, but it does admit a modular completion, non-holomorphic modular completion, something which depends on tau bar, which we denote again by phi hat in the same way we did it for the mock modular forms of single variables. And one can similarly define a modular completion of this upper Lurk sum. And both these completions are non-holomorphic in tau, but transform like a proper Jacobi form of weight 2 and index m. Okay. So that leads to this new mathematical object which we introduce, a natural definition of a mock Jacobi form. If you recall, a Jacobi form, by using its modular properties, using its elliptic properties, admitted an theta expansion. So basically, this theta function takes care of its translation properties under z going to z plus lambda tau plus mu. Basically, the function is invariant up to some phases, and the theta function has exactly the same phases. Theta function is also constructed in such a way that it has the same translation invariant properties up to a phase, and what you're left with are these vector valued mock modular forms. So the definition of mock Jacobi forms is very similar to the definition of Jacobi forms. In the case of Jacobi forms, HL would have been ordinary modular forms, vector valued modular forms. For mock Jacobi forms, it is vector valued mock modular forms. And therefore, HLs admit a completion HL hat with some GL star by adding some piece called GL star, and it would transform as a weight 3/2, because you see theta has weight half, so plus this has weight 3/2 to give you 2 on this side. The total weight is 2, which is half plus 3/2. So it is a weight 3/2 modular form. The completion transforms in that manner, but it has a holomorphic anomaly. So if you recall, once again, we had this kind of a exclusive OR property that either you can have holomorphy, modularity, or pole free or simple. You cannot have all of them. You can only have 2 out of these 4 properties. And the holomorphic anomaly is particularly simple. It's itself given in terms of the theta function that we introduced, evaluated at z is equal to 0. This is a theta function depending only on tau. And now, given the theta expansion, you can sort of put back the theta expansion, and therefore you can construct a modular completion of the mock Jacobi form, which will have this holomorphic anomaly equation. So this is what we had done yesterday. So I'm just very quickly reviewing it because you might have forgotten some of these things. Now the question becomes, given a shadow, suppose I give you a mock modular form with completion f hat, and you don't know what f is, but you know the shadow, right? So all that you know suppose you know some equation like 4 pi tau 2 to the power k del by del tau bar of f hat is equal to say 2 pi g bar. And clearly, from this equation, one can find there could be some f for which f plus g star has a nice modular properties. But I can always add to it, say, of weight k. But I can always add to f plus some other proper modular form. So f is a mock modular form. But to the mock modular form, you can always add a proper modular form. And still, its modular properties will not change, and the holomorphic anomaly equations will not change. And therefore, there is an ambiguity in determining what is f. But one can ask the question, what is sort of the optimal mock modular form that you can think about? Optimal meaning one whose Fourier coefficients grow as slowly as possible. So what you can do is that given a particular shadow and a particular modular form, mock modular form, you can try to subtract from it as much sort of normal modularity as you want to be left with some kind of a absolutely essential mock modularity that you would like to be left behind with. Okay, so using this ambiguity, what you would like to do is that given a mock modular form, you can ask the question, can I associate some kind of an equivalence class of these mock modular forms such that there is a member whose Fourier coefficients grow as slowly as possible? And that you can call as the optimal mock modular form of a given shadow. And the answer to that question actually turns out to be very interesting in the black hole context. And I want to go over it a little bit because it's also the example that comes up in the gauge theory context for completely different reasons. And that's the example that Powell will talk about in the context of supersymmetric Yang-Mills theory. So let's consider the special case. So we had a very general decomposition theorem for psi m. And for psi m, we had a very general shadow like that. But now you can take m to be 1 in this equation. And you will have a particular shadow. And the shadow, it will be theta 1, 0 and theta 1, 1. There will be two shadows. Because remember, L goes from 0 to 2m minus 1. I mean, L takes values, 2m values. L is 0, L is mod 2m. So if m is equal to 1, it can go from, L goes from 0 to 2m minus 1. So you can ask the question, what is the optimum modular form? What is the optimal mock modular form H0 and H1? Whose shadow is this? And the answer to that question was found by Zagier for his own reasons. And it relates to some very intriguing mathematics in number theory. I mean, some intriguing number theory. And it turns out that optimal mock modular form, which grows very slowly, is given in terms of these Fourier coefficients, which are called class numbers. So H4n and H4n minus 1 are called some specific class numbers. Okay, so quite this innocent looking meromorphic Jacobi form somehow suddenly leads to all these kinds of very rich mathematics. And these are called the Hurwitz-Kronecker class numbers. And they are defined in some way. You don't need to really know if you are not doing number theory. There are some kind of SL to Z equivalence classes of some integral binary quadratic forms of discriminant minus n. Okay, if some of you are interested in it, they can read my notes, or they can read the original DMC paper or original paper of Zagier, in fact. And basically, it is 0 unless n is equal to 0 or minus 1 modulo 4. So that's the situation that we are interested in. And sorry, perhaps I went too fast here. Here, okay. So now look here, the completion therefore depends on these Hurwitz-Kronecker class numbers, which is the mock part, and there is a non-holomorphic part. And you can see that if you take del by del tau bar of this h0 tau, you'll get something like q to the n square. And that's nothing but theta 10. Theta 10 is, and in the other case, you'll get q to the n plus half square. Okay, so this is a very simple, what is called the theta series, with consisting of just Gaussians, or Gaussians or quadratic q to the power n square or q to the power n plus half square. It's a very simple natural theta series that appears, and somehow the black hole problem leads to this particularly simple mock modular form, which also has interesting number theory, but it will also make its appearance in a very different context of the partition function of Yang-Mills instantons.
There is a couple of questions in the chat.
Okay, I think this is a good point to stop.
So one question is from Nava Gadam. What is the physical interpretation of the shadow, both in the black hole context and in the gauge theory context?
Yes, so as I told you, the physical interpretation has something to do with some kind of non-compactness, and that's the topic of my remaining half of my lecture. So I will come to that.
And the other question from Himanshu. In the black hole context, to write the decomposition theorem, we do not need to use the fact that the individual pieces are mock modular, right?
No, so the point is that given any function, you can always decompose it into two other functions, right? That's a triviality.
Yes, but you said it's a unique decomposition. So it's
the unique decomposition means that you can decompose it in terms of an Apple-Lurk sum and a mock Jacobi form.
But that's just saying that one part is singular and one part is finite, and that
yes, yeah. So one part has exactly the same poles as your original meromorphic Jacobi form, and it is an Apple-Lurk sum constructed out of the average of these poles, right?
Yeah.
Right. So it's a very specific unique decomposition.
But
yeah, you can. Yeah, there are infinite number of decompositions you can do of this kind, of course. The point is that this particular decomposition, where you separate polar and this in a particular way, such that the polar part has the elliptic properties that you want, then you are left with a mock Jacobi form.
But it does not require, like, I mean, it's just a consequence, right?
It's a statement of the content of the theorem is that if you give me a meromorphic Jacobi form, then I will create out of it a mock Jacobi form. Because I will just look at the poles of that meromorphic Jacobi form. Okay, and I will take the elliptic average of the poles. That is called the Apple-Lurk sum. And then I will take that object and subtract it from your original meromorphic Jacobi form. And whatever I'm left with is a mock Jacobi form. That's the statement.
I see. Okay.
Meaning that particular object has no nice modular properties. However, it is possible to add to it a shadow, some kind of G star, something constructed out of the shadow, such that the completed object has nice modular properties.
Okay, thanks.
And this has a very important physical consequence. You see, it's not just something mathematical, because after all, this is related to holography. The Fourier coefficients of the mock Jacobi form are unambiguously defined, and they count the degrees of freedom of a single centered black hole. And in many situations, a black hole, if you remember the Strominger-Waffa story, I don't know if, but you can think of a black hole. Suppose you have a black hole in 4 dimensions. You can think of as coming from a black string in 5 dimensions. So you take 5-dimensional theory and compactify a circle along which the string is wrapping. And the oscillations of that string gives rise to would look like a point object in the remaining directions. And if you think about it like that, then the near horizon geometry of a black string is ADS3. And as we know, it has to have a CFT2 dual. And that CFT2, you can calculate the index partition function of that theory. And that should give you the degeneracies of the black holes in the theory. Because the ADS3 is, as you know, is like a solid cylinder. And inside that you have some BTZ black holes. So the 4D black hole will look like an near horizon ADS2 region. Has a near, so near horizon, a 4-dimensional black hole will look like ADS2 cross S2. And a black string would look like ADS3 cross S2. This BTZ black hole you identify with your original black hole. And therefore, the counting function of this CFT2, the elliptic genus of this boundary CFT2, should give you the black hole degeneracies. And that is naturally you would like to identify with the mock Jacobi form. And then the question arises, what is the physical origin of this mock behavior in this physical context? And the same problem you can ask, another way to ask is that why is the elliptic genus of this boundary CFT not holomorphic? So for a compact CFT, the elliptic genus is independent of tau bar by the standard argument, which we discussed yesterday in the tutorial, that the right moving, it's like counting the right moving ground states, because the right moving Bose and Fermi states with non-zero right moving energy, they are paired by supersymmetry. So for the right movers, if you have a bosonic state of energy not equal to 0, then by acting with a Q, you get a fermionic state. And the fermionic state has you are computing trace of -1 to the F, e to the minus beta E. So it's you can write it as a sum over. Suppose you have a discrete spectrum with a sum over e to the n. And as long as En is not equal to 0, then bosons and fermions are, the states are paired, and from this trace they will contribute 0. Whereas if you have E0 equal to for E0, which is 0, if the supersymmetry is not spontaneously broken, then because the Hamiltonian is Q square, if Hamiltonian vanishes, Q acting on this state also vanishes. And therefore it is perfectly possible that ground states are not paired. The Bose-Fermi pairing is not required for the ground state. So it's perfectly possible that you have 3 bosonic ground states, but no fermionic ground states. Whereas for non-zero energy, it has to be the case that if you have 3 bosonic states of energy, some particular value, non-zero value, you have to have 3 fermionic states of the same value, eigenvalue. Okay, so this is the situation for the non-compact CFT. And as we will see, the non-holomorphy is a consequence of the failure of this naive argument. In a non-compact theory, one can have a continuum of states, and the density of states of bosons and fermions need not exactly cancel. So we did this yesterday in the tutorial a little bit, so I can go over it quickly. One can now define, we are trying to understand anomalous tau bar dependence. If we understand the anomalous tau bar dependence, then we understand mock modularity from a physical point of view. Okay, at least part of it. So we want to understand, why does this completion? So the completion is the object that appears in a physical computation, because physical computations which give you physical observables should exhibit the symmetries of the theory. So if S duality is the symmetry of the theory, or SL2Z is the symmetry of the theory, if you compute some physical object like a path integral of a partition function, then you expect that it has to have the SL2Z symmetry. So it has to be modular, but it does not have to be holomorphic, because this naive argument can fail. So in this way, we rescue the situation that we managed to sneak in non-holomorphy so that the physical symmetries are preserved. So anomalous tau bar dependence of some elliptic genus, we will relate it to much simpler problems. So elliptic genus is in some 1+1 dimensional conformal or 2-dimensional conformal field theory. Is defined in a 2-dimensional quantum field theory. You can relate it to anomalous beta dependence of Witten index in supersymmetric quantum mechanics, which you can think of as 1+0 dimensional quantum field theory. And in fact, actually by localization, it will turn out many calculations in higher dimensional gauge theories and so on will reduce to this one-dimensional example. So actually this one-dimensional example is quite crucial. And I would like you to understand it well, because if you understand this example, you'll more or less understand physical origin of mock modularity. Okay, so let me just run over the argument for a compact theory. By compact theory, what do we mean? You can compute the Witten index, take a supersymmetric quantum mechanics. So supersymmetric quantum mechanics means just a point particle moving on some manifold, right? So you have some manifold M, and there is a point particle moving. It's a world line moving in this manifold, and you're computing some trace over that. It's some closed loop, and you're computing that trace, right? And typically, if you calculated, say, the Hamiltonian of such a theory, suppose you have a point particle moving on some manifold. So maybe I should switch to, so let's just consider a point particle on some manifold X with some metric Gij. Then the simplest action you can write down is Gij x dot j x dot I half. This is like the kinetic term. This is the Lagrangian. So the Hamiltonian is basically p square. Let's first consider a flat space. Okay, so for a flat space, Lagrangian is just x dot square over 2, where x is the coordinate, and Hamiltonian is just p square over 2, right? In which, if you quantize it, it just becomes minus del square over 2. So this is basically the Laplacian. So studying a quantum mechanics of a point particle on a manifold is equivalent to studying the eigenvalues of the Laplace operator. Now, if you put supersymmetry in it, you can put some psi I, deep psi I dt, you make it supersymmetric, plus dot dot dot. And you quantize this psi I, then you get psi I psi j is equal to delta ij. You know, if you impose canonical commutation relations, and this looks like Clifford algebra. This looks like gamma matrices. And there is a supercharged Q, which is like psi I pi, which looks like the Dirac operator. Because psi I become like gamma matrices and pi becomes like del by del xi. Now, if this manifold is compact, the spectrum of its Laplacian is discrete. And then Witten's argument would kick in, and you can show that W of beta is independent of beta. But I will write it in a form that you will recognize as an anomaly equation. So for example, if X is some torus, 2 torus, or X could be K3, you'll always get this equation will be satisfied. And this is actually the key to the proof of say many important theorems like Atiyah-Singer theorem using supersymmetric quantum mechanics, going back to Witten's famous work. Now, if X is non-compact, there is an anomaly. And the anomaly is d by d beta of W beta is something else, is not equal to 0. And if you can calculate this, and if you can relate it to one of these error functions that we were observing, sorry, I mean, if we get the equation similar to what we were getting in the mock story, then we have understood the physical origin of mock modularity. And that's what we will do. Okay. So to do that, I'm going to actually take even a simpler case. See, we went from 1 plus 1 dimensional theory, or a 2D quantum field theory. We went to 1D quantum mechanics. So remember, this 1D and 2D refers to the base manifold. And that can be, there is a target manifold, so don't confuse the two things. So for example, QFT means that it's like a string moving in some target manifold. There is a string moving in some target manifold. That is the original problem for the elliptic genus that we were interested in, right? We were computing the partition function of some conformal field theory, which you can think of as something living on the world sheet of a string moving in some target manifold. So this we reduce to the problem of a point particle moving in that same target manifold. And now, instead of doing quantum mechanics, you can just do ordinary integrals. And that would be the zero-dimensional. Zero-dimensional QFT. This is just quantum mechanics. Quantum mechanical path integral. Sorry, one-dimensional QFT is just the quantum mechanical path integral, gives you a quantum mechanical path integral. Whereas if you take zero-dimensional quantum field theory, then that just gives you an ordinary integral. Because see, what do you mean by zero-dimensional? That this, you have some variable x, it's a function of tau here. Here it's a function of tau and sigma. But if it's a zero-dimensional quantum field theory, then x is a function of nothing. It's just a number. Therefore, instead of getting a path integral dx mu, dx of tau, you just get an ordinary integral dx. So I'm going to take a very simple example, and then I will stop of such an example. Before I go there, what I want to say is that if you have a trace like that, w of beta, trace -1 to the f, e to the minus beta h. And if you remember your quantum field theory, you can always write this as a path integral over some classical action. The classical action will depend on some fermionic variables as well, psi of tau. And you use periodic boundary conditions. This trace -1 to the f means that not only the bosonic fields, but also the fermionic fields have, so you have dx and then you have deep psi. Such that the action is evaluated on a circle of periodicity beta. So action is evaluated on some d tau times x dot square over 2 plus dot dot dot, going from 0 to beta. Okay, so it's a periodic with periodic boundary conditions and something evaluated on a circle. This is something that you're familiar with. So now with this understanding, basically you understand that the Witten index can be related to some supersymmetric path integral. And if you now take the zero-dimensional version of it, so more generally, an elliptic genus would be related to a path integral of a two-dimensional quantum field theory. So in that case, your x and psi will depend on tau and sigma, which are the world sheet coordinates. If you have just quantum mechanics, then there is no sigma variable. It will just depend on tau. And if you just have a zero-dimensional path integral, it doesn't depend on anything. So it's just an ordinary integral. So with that understanding, let's just go back to this example that I wanted to. What happened? Sorry, I want to go to here. So let's consider a particularly simple path integral. Let's look at this path integral. Okay, so you have one bosonic variable u, two bosonic variables, and two fermionic variables. And the action now is not an integral. The action is just a function. It's f square plus f of h prime u plus I h double prime psi minus psi plus. You can check actually this action is supersymmetric. It has some supersymmetry which I will not write. So there is some Grassmann, there is some supersymmetry transformation of delta psi going to x and delta x going to psi, which exchanges bosonic and fermionic variables. And that's the symmetry of this action. Okay, so it's a very simple action. It's a Gaussian with f square. It depends on some arbitrary function h of u, and one can choose h prime of u to be some very simple function lambda tan hu. So h prime of u is some function like that. It goes from minus lambda to plus lambda. Okay. And now you can try to evaluate the path in this path integral. It's pretty easy to do this path integral actually. What happens is that if you do the psi minus psi plus integral, you'll get something like h double prime u downstairs. And if you do the f integral, you'll get something like e to the minus h prime square upstairs du. That's the integral you are left with. You can just make a change of variable y is equal to h prime of u. And then you will get this Gaussian integral. And if you evaluate at w infinity, you'll get 1. Because when beta goes to infinity, you'll just get a Gaussian going from minus infinity to plus infinity, which you can evaluate, properly normalized. So the main point is that because this function is going in this particular way, y does not go from minus infinity to infinity. See, so this is your u coordinate, and this is h prime of u. So h prime of u is the same as y. So you can see that as u goes from minus infinity to plus infinity, y goes only from minus lambda to plus lambda. And because I have put in some square root of beta by 2 just for simplicity, it basically goes from minus square root of beta by 2 lambda to plus square root of beta 2 by lambda. So it's an integral which is integral of a Gaussian, which we know very well how to do, but over a finite integral, which we don't know how to do, but which is given in terms of the error function. And that is where the error function comes into the story. Okay, and this error function is nothing, is related to the gamma, incomplete gamma function. And that is the incomplete gamma function which we encountered in the completion. If you remember, the completion of various things that I discussed, I'm going to go back, sorry. For example, here we had some incomplete gamma function. That incomplete gamma function is nothing but the incomplete gamma function we're encountering in a very different context of a Witten index of a non-compact theory. And that is the connection between mock modularity and non-compactness. I don't think I have the time to describe it in greater detail. So I think I will probably, it's probably a good time for me to stop. It has all kinds of interesting consequences. But maybe I should stop here.
Okay.
Yeah, so just to conclude what we have seen, maybe I'll stop here. Sorry.
So you finish your lecture, you mean?
Yeah, maybe I will just. Yeah, there might be questions, right? So I should leave some time for the questions.
Okay.
So let me just finish by concluding. As we saw, inspired by Ramanujan's, kind of very inspired guess about some very interesting functions, mock modularity entered mathematics. And okay, people like Dyson wondered where it would come into physics. And we have seen in the last 10 years or so, it has slowly seeped into physics in a very interesting way. And my first encounter was in the context of black holes, in the holographic, with this paper of Murthy and Zagier. But then later on, we also encountered in topology when we were trying to compute and other people also, when people were trying to compute elliptic genera of non-compact theory. And more recently, we also understood from a path integral perspective how this mock modularity and the shadow and the holomorphic correction arises in a very different physical context of four-dimensional quantum gauge theories. And a common link between all of them is that everywhere in all these problems, in holography, there is a boundary CFT. In topology, there is a CFT whose elliptic genus you're trying to compute, which is also non-compact. And as I saw, even in a simpler context like a Witten index, which has nothing to do with modularity per se, very similar functions like error functions appear. And in duality, it's a four-dimensional gauge theory where the SL to Z symmetry is a S duality. But as Pavel might explain, if he has the time, if you think of it as coming from a Euclidean M5 brane, then you can consider an Euclidean M5 brane wrapping a 4 manifold times 2 torus. And depending on whether the 4 manifold is small or the 2 torus is small, you can either regard it as a 4-dimensional quantum gauge theory or a 2-dimensional sigma model. So secretly, there is another 2-dimensional quantum field theory there, a conformal field theory there. And that also turns out to be non-compact. In all these 3 contexts, mock modularity sort of forces itself upon you, because otherwise some important physical symmetries of the problem seem to be lost. And to restore them, you have to use this modular completion with some non-holomorphic terms in it. And those can now be derived from a physical point of view using relatively simple calculations of a path integral. You just calculate the non-compact contributions from the path integral, and that exactly precisely reproduces the shadows that are required. And in particular, in this duality case, you can derive it more or less completely explicitly. Completely explicitly with all the factors and everything. And this is what Pavel will describe. So I think I will stop here.
Okay. Yeah, we can thank Atish by unmuting.
Okay. So I'm.
Yes, there's a question from Himanshu.
Yeah. So what is non-compact in this 0-dimensional example? In 2D case, I thought you mean that the world sheet is non-compact.
No, not the world sheet. The target space is non-compact.
So in the
No. So when I say non-compact, it's always the. Okay. So non-compact.
F going to marathon. Sorry.
So non-compact. See, yeah, don't get confused between. There is a base manifold which can be a T2, S1, or just a point. Okay, and the base manifold is always compact. If you take a superconformal field theory and do a path integral, so basically from here you can have a map into some manifold M, which is the target manifold. Think of a string theory, right? String theory is a 2-dimensional world sheet. If you're computing a, say, 1-loop string theory calculation, then you're taking a map from T2 to a 10-dimensional target space-time, which could be 4-dimensional flat space plus 6-dimensional Calabi, or cross 6-dimensional Calabi, or K3, or whatever. So this target space can be compact or non-compact. Okay. Now, depending on that, let's just, if you have just think about quantum mechanics, right? If you take a quantum mechanical problem, just a point particle moving in a 4-dimensional, say 4-dimensional R4. R4 is non-compact, right? And what is the Hamiltonian of a point particle on R4?
Just Laplacian.
It's just Laplacian, and whose eigenvalues are p square, which form a continuum, right? They are not discrete. So now if you calculate a trace of the Hamiltonian, you'll first of all you'll get a divergence. Okay, that's a separate story actually. You'll get a volume divergence that you have to regulate. But if you compute some index partition function, that volume divergence is not there, because there is a Bose-Fermi cancellation, little bit of Bose-Fermi cancellation. But when I say compact or non-compact, I'm always talking about the target manifold.
So in the 0-dimensional example, the fact that F goes from -infinity to infinity is a sign of non-compactness.
Yeah, you know, the U coordinate in the U coordinate went from -infinity to +infinity, and the Y coordinate after the change of variable, right, went from -β/2 square root of lambda to plus square root of β/2 lambda, and that gave rise to the error function.
I see. Okay. Thanks.
Any more questions?
Yeah, I think I have some of these things, all these other things Pavel will talk about. Well, not all of them, but okay, some of them.
Okay, there is a question from Arif Mort. Yeah, please go ahead.
Hi. Could you tell us something about the multi-centered black holes that you talked about that in the wall crossing phenomena? That when you're counting the degeneracy, then when the moduli space crosses the wall, then you want to discount. You don't want to count the contribution of the multi-centered black holes that led to the decomposition of the.
Yes.
So now these multi-centered black holes, is it like several horizons at different places in space-time? And
Yes. Basically, you can have one black hole here, and another black hole here.
how should I think of it?
Yeah, one black hole here and another one in Andromeda galaxy.
Yes, but my question would be: are these inside the black holes? Are they connected?
No, they're not connected. I mean,
so the two horizons.
No, like our universe has many black holes, right? Now, in our universe, there's black holes.
Well, I want to differentiate between two things.
Yes.
So say you have a pair of black holes, but then their inside is connected by a wormhole. Versus
not necessarily.
when you do not have, you have just separate black hole.
Yeah, exactly.
Yeah, no, but then the difference would be a factor of 2. Yeah, but the difference is the factor of 2 in the degeneracy, because if you have two black holes separately sitting there, the entropy is, twice of area by 4. But if you have two black holes, but they are connected by a wormhole, then the entropy is just area by 4.
Yes, so these black holes are not connected by wormholes.
How do you differentiate between the two?
Yeah, so they are not connected by wormholes. I mean, such solutions don't exist in this theory. See, it's a supersymmetric context, so you can actually work out all the solutions explicitly. So in particular, if the degeneracy of this black hole is dn1, so d1, sorry, it turns out that this black hole is electric, has only electric charge in particular frame, and this black hole is only magnetic charge. Okay. So you can ask, what is the total degeneracy of this configuration? It would be d1 times d2, right?
Right.
If they are independent of each other.
Okay. Yeah.
Actually, additional contribution because of the fact that if you know there is a Saha effect, that if you have a magnetic monopole and an electric charge going around it, right? Then there is if you look at the Poynting vector, there is an angular momentum in the system. There is a field angular momentum. And corresponding to the field angular momentum, there is an additional factor, some 2L plus 1. There is a factor L. The total but this shows that these black holes are not connected in any way. They are completely independent objects. Each has its own degeneracy. If you put them together, the total degeneracy is the product of the two degeneracies, up to a small correction factor coming from the fact that you are in some you have some additional degeneracy from the angular momentum of the field.
Okay, good. Yeah. All right. Thank you.
Any more? Okay, there is a question from Kyron Soon. Please go ahead.
Hi. I have a question. So yesterday you mentioned the two generators of the holomorphic weak Jacobi forms. They are the elliptic general of torus T4 and K3.
Yes.
So we know that this kind of holomorphic weak Jacobi forms are actually the well-environmental Jacobi forms of SU2, right? So this can be.
So first of all, these are not weak Jacobi. No, the theorem was about holomorphic Jacobi forms, not about weak Jacobi forms.
Okay, holomorphic Jacobi forms. So my question is, we know that the holomorphic Jacobi forms can be generalized to put it on arbitrary root lattice of simple Lie algebra, right?
So you're saying that instead of considering, what that means is that we had this function a and b as a function of tau and a single complex variable z.
Yes. My question is,
you can generalize this to a and tau as a vector of Z, for example.
Yes, yes.
Is that what you have in mind?
Yes.
Yeah, in that case, I don't know. Yeah, I think there is no, I'm not aware of such a theorem, a general theorem in that case. I mean, it's partly because it has not been studied, but I would not be surprised. No, I mean, the thing is that then the situation is more complicated, right? Suppose you have Z1 and Z2.
Yes, yeah, I know the generators for this kind of thing. My question
You
is,
do? Okay, okay.
my question is whether this kind of generators are also some elliptic general of some.
Yes, yes. They actually occur very naturally for the MSW string. You see, the point is that what we did was that the left moving theory, okay. So you had how did we define the elliptic genus, right? The elliptic genus was trace -1 to the F, sort of Q to the L0, Q bar to the L0 bar, -1 to the F bar, and then -1 to the F, and Y to the power some J.
Okay.
Where J is some left moving current. But you can clearly imagine a situation where you have J1 left, J2 left. You can have many U1s on the left hand side.
Okay.
In that case, you will have some fugacities Y1, Y2, Y3, which will be 2 pi I Z1, 2 pi I Z2. Right? So you can compute a more generalized partition. I mean, another way to say that is that in the case of 2,2 theory, there was a natural U1, which was the R symmetry of the 2,2 theory. But you can define a more generalized elliptic genus where you have a 0,2 theory and large number of U1s on the left hand side.
So you mean the manifold is still T4 and K3?
No. More general manifolds.
Okay.
In general, I mean, so this will typically arise in the context of the MSW string, for example. So you can, I mean, don't think about a manifold. Think about the superconformal field theory with 0,2 symmetry. Okay. Now, you can, in addition to the Virasoro symmetry on the left movers, you can have some U1 Cox-Moody symmetry, and you can have many of them. You can have U1 prime, U1 double prime, or with charges J left 1, J left 2, etc. And then you can define a generalized elliptic genus of the kind that you want.
I see.
So it's a very natural thing to consider, this multi-variable generalization of a, instead of considering a tau and Z, you can consider tau and a vector Z.
Okay, I see. So for example, for SU3 case, there are 3 generators. So you mean currently we still don't know what's the physical meaning of these 3 generators?
I'm sure there is a nice physical meaning of it.
Okay.
I mean, what I'm saying is that, okay, not all generators always have a nice interpretation, but for SU3, maybe there is. I mean, I would not be surprised.
Okay, thanks.
Any more questions? Okay, then I think we can thank Atish again for his nice 2 lectures. And yeah, we will reconvene in roughly 15 minutes with the second lecture by Ahmed Al-Khmiri about quantum black holes.
Okay, Pavel, I'm done. It's your.
Okay, thank you.
Thanks. I will go get some coffee.
Yes.
Hello.
Ahmed.
Hey. I wanted to test something. Can I share my screen?
Yes, you should be able. Yeah. Yeah, I see your window.
Okay. If I, let me see. Do you see?
Now it's just kind of 2-page.
Yeah. Is it filling your screen?
Yeah, I think it's yeah, almost fit. Yeah.
And is it legible? Like, is it too small or is it okay size?
Well, I think it's fine, but I have to. Well, I have to make it full screen for me to make it legible. But it's possible to make it legible. Yes. But it might also depend on the internet connections of other people. But
Okay.
but in principle, it's yeah, it's readable. Even the smallest.
Okay. I'll go with this, and then if I get complaints, I'll I can always zoom in. Maybe that's too much.
Yeah, you can share again if you want.
Okay.
Well, there's 2 more minutes.
Okay.
Hi, Ahmed.
Hey, Dish.
Okay, I think we can start. It's a pleasure to have Ahmed Alkhmeri with his second lecture on quantum black holes.
All right, thanks, Pavel. Let me see. So let me begin with a quick recap of what we did last time. So last time was pretty much all set up. The system that we're setting up to study or to analyze more is what I have here on the right-hand side. Actually, first, let me just say something. I'm putting 2 pages at the same time to minimize sort of motion. And so if anything is small and you can't read it, please let us know. Okay, so as I was saying, the setup that we were constructing was this eternal black hole that's in thermal equilibrium with this bath system. And the claim is that one can learn a lot about quantum black holes from this setup. We talked about the stress energy profile everywhere, and we also discussed what the quantum state is of the matter living on this hybrid ADS flat spacetime. We showed that you can think of the quantum state as being a vacuum state in a different conformal frame, which is defined by this coordinate W. And this will get us a lot of mileage, as you will see in a bit. So again, the other thing that we talked about was the computation of the von Neumann entropy for a CFT state on flat space in the vacuum. We reviewed that, and we showed that if you compute the entropy of an interval using the replica trick, or any number of intervals, it's given by some, well, the Renyi entropies, these trace rho to the n's, are computed by correlation functions of twist fields. So for a single interval, it was a 2-point function. And for 2 intervals, it was a 4-point function. And these twist fields are primary operators with some dimension. And you can just compute, at least for the single interval, you can compute the entropy exactly. It's given by this formula here, log C over 3, C is the number of fields, log L is the length of the interval, divided by some cutoff factors at the 2 ends of the interval. Now, let me discuss how to apply this formula to the case at hand. So let's focus on the left page. So the way to do it is, again, to take advantage of the fact that the state can be mapped to the vacuum in some conformal frame. So we start with our physical setup. That's in picture number 1. So suppose we want to compute the entropy of some interval that I've shown here that goes from y1 to y2. These y1s and y2s are the, again, coordinates in the physical spacetime. So we pick the coordinates and we pick some cutoff. And the most sort of appropriate choice for the cutoff would be some length or some proper distance in the physical metric. So here, that's what I wrote down here. ds, which is just the square root of ds squared, is going to be equal to, by definition, the square root of epsilon 1 y plus, epsilon 1 y minus. So there's an epsilon, there's a cutoff for each null coordinate. Okay, so that's the interval in the physical spacetime. Now, to compute what that entropy is of that interval, the first step is to map the problem to the conformal frame where the state is the vacuum. In this coordinate system or frame, we know what the entropy is, right? It's just, it's going to be, well, it's C over 3 times log L, but now I'm writing this in terms of L squared, so that's why it's a C over 6. So it's a C over 6 log of this is the proper distance squared in the W coordinates. So it's W plus at Y1 plus minus W plus at Y2 plus multiplied by the same thing, but with all minuses, right? Because the metric, if you recall, is just dW plus dW minus. So it's the interval in the plus coordinate times the interval in the minus coordinate. And then you need to divide by the cutoff factors at the two ends. Okay, so far this is just a formula that we saw in the previous page. Okay, so and this can be expressed in terms of the coordinate y, because we know what the transformation is between W and 1. The subtle thing here is these cutoffs. So as written, these are the cutoffs in the W frame. But in order to get an answer that corresponds to the physical spacetime, you need to transform the cutoffs to those calculated with respect to the metric in the physical spacetime. So, for example, if we focus on the metric or the coordinate transformation in the Bath region, so we can express the metric in the W frame as some conformal factor multiplied by the metric in the Y frame. So here I just did a coordinate transformation. Okay, and so this tells you now that the proper distance in the W frame, which is equal to epsilon W plus epsilon W minus, is equal to some conformal factor multiplied by the proper distance in the physical Y frame. Okay, so that's how we relate these two cutoffs. And similarly, if you have, for the point in the bulk, again, the W frame metric is equal to this horrible conformal factor multiplied by the physical metric, the ADS2 metric in the bulk spacetime. So again, this is the relation between the cutoffs. So essentially what you need to do is you need to take this formula for S and plug in for this epsilon W with this horrible expression. It's not that horrible, but yeah. So some conformal factor times epsilon Y. And that's how you get the formula for computing entanglement entropies for intervals in the physical spacetime. Let me pause here for 5 seconds for questions.
Yeah, there is one question I got in the chat from Erez Urbach. At step 2, you use the QFT result, but inside you also have gravity.
Good. You're looking really far ahead. So the approximation in which we are working up to this point is the semiclassical approximation. What that means is you just have quantum fields propagating on a fixed background, on a fixed metric. So gravity has been, in some sense, turned off at this point. I can't hear you, Pablo.
Sorry, yeah, I was. Yeah, so there is right hand from Arif Mort. Yeah, please unmute yourself and ask.
Okay. So when you go back to the Y frame from W frame, then this innocuous, it's just change of coordinates. However, it also changes the state, right? So would you still be computing entropy of the vacuum, or now this will be now the entropy in the new, whatever the state is now?
Yeah. So good question. So there is some state in this geometry. In step 1, in the physical spacetime, there is some state. Maybe you can, it's some state. It's not necessarily the vacuum, but I think by some definition you can call it the vacuum. But the point here is that we know precisely what the state is in a different frame. And so the trick is to go to that frame, compute whatever you want to compute, and then we know how the entropy transforms under a conformal transformation, which is what I did here with the epsilons. So you go to this W frame, you compute whatever you want to compute, and then you transform back. And you have to transform your quantities that you computed in the right way, and then you know what the answer is in the physical spacetime, in whatever the state is on that physical spacetime.
Gotcha. Thanks.
Yeah.
Any more questions? No, I think it's okay.
Okay,
I
great.
have a question about this cutoffs. So usually in a Euclidean CFT, we have only one cutoff epsilon. Is there any reason you are choosing these two epsilons? Because they belong to two different, one in flat and one in ADS, something like that?
So usually you have a single metric everywhere. The metric is just flat everywhere. But in this case, the metric is different in the two regions, in the ADS region and in the flat space region. That's why the cutoff is quote unquote different, but really the more invariant way of defining the cutoff is in terms of proper distance of where that point is or where that cutoff is. And so by that definition, you can say that it's actually the same cutoff everywhere. So maybe, so you can, yeah, the size of the cutoff in proper distance units is the same at 0.1 and 0.2. Well, you can just pick them to be the same. Let me see if I can explain this a bit better. So if you look at this formula, we have an epsilon1 and epsilon2. So epsilon1 is, according to my picture, is the one in ADS. So epsilon. So here in the bulk calculation for the cutoffs, there's an you can label this as epsilon1. It's going to be some function which depends on y1. But this proper distance is just some epsilon y. There's no 1 or 2 in it. And similarly, when we compute the cutoff in the Bath region, this is going to be some epsilon 2. Then it's going to be some conformal factor, which depends on the location y2. But then this epsilon can be the same as this epsilon. So you can be consistent by choosing that the proper distance cutoffs near y1 and near y2 are the same in the physical metric near those points. Did that address your question?
Yeah, thanks.
Yeah.
Okay, so yeah, there is one more question in the chat from Hamid Afshar. Is entanglement entropy quasi-primary under the conformal transformation?
And maybe you can think of it like that, but if you were to think of the previous step before computing the entanglement entropy and looking at the Renyi entropies, so the Renyi entropies are just correlation functions of primary fields, actually truly primary fields. And so they just transform as primaries, and then when you compute the entropy, it's going to transform in the way that I described here.
Okay, I think that's it.
Okay. Okay, great. So, okay, so that's really everything about the setup. Now let's try to analyze this model to death and show that it has really interesting physical properties. Let me see. So I claim that this black hole has an information paradox, and with all the difficulties that come with usual black holes that you can sort of collapse or form by collapse and let them evaporate away. But in this setup, things are much simpler because the space-time is static. That's why it's a good toy model. Okay, so here's a space-time again. It's a bit busy, but let me explain it. So the first point is that we know that the quantum state can be described as having these entangled pairs entangled across the horizon, where you have these sort of right-moving pairs entangled across this horizon and left-moving pairs entangled across this horizon. And they're sort of arranged symmetrically about these horizons. This radiation, the part of it that's going out from the ADS region to the bath region is the Hawking radiation, and the part of it that's falling in is the thermal flux of the bath, keeping the black hole in equilibrium. Now we want to compute the analog of, well, when you have an evaporating black hole, you want to compute the entropy of the radiation. So what's the right part of the space-time whose entropy can be thought of as the entropy of the radiation? I claim you should consider the union of these two regions in the two bath flat spacetimes, which we can label as B. Okay, so this region here, the union of these two is B. And to study the behavior of the entropy of this interval as a function of time, we will study what happens as both of these endpoints are moved upwards as shown. Okay? So what happens here is as you move these two intervals up, it collects Hawking radiation, and so then the entropy of this region as a function of time can be thought of as computing the entropy of the Hawking radiation. Okay, so very good. Oh, sorry. Okay, so I claim that the entropy of rho B of this region grows linearly in time for all time. Let me give you two arguments. The first argument is a schematic one. So entropy of this region is going to grow due to the sort of collection of Hawking quanta. Sorry, this thing is not, there you go. Yeah, okay, sorry. The entropy is going to continue to grow because it captures more and more Hawking quanta that are entangled with the interior quanta behind the horizon. Okay? Maybe I should go, I'm going to go back to this slide again. So if you see, as you move upwards, you collect more Hawking quanta that are entangled with the interior ones. Okay? Or if you look at the left movers, so this mode is contained in B, but this mode leaves B. And so that's why the entropy would also grow. So again, it's the same reason. And since these Hawking quanta are generated at a rate given by the temperature of the black hole, which is constant for all time, then you expect that, that the entropy is just going to be the rate multiplied by the time. So the rate here, there's a C, which is a central charge. It just tells you the number of different fields multiplied by 1 over beta, which is the temperature, times the time. Okay, so that's the quick argument. A more careful argument is to just compute the entanglement entropy using all the technology that we've developed. The idea goes as follows. So we know that by purity of the global state, so the state of the quantum fields on any Cauchy slice going from one spatial infinity of one bath to the other spatial infinity of the other bath is pure. So that state is pure, and so the entropy is 0. Then we can use this relation of entanglement entropy, or this identity of entanglement entropy, that if you have a bipartite system that is in a pure state, so SBB bar is equal to 0, then you can show that SB is equal to SB bar. S of the interval is equal to its complement. This means that we can, instead of computing the entropy of this region, we can look at its complement, which looks something like this. And so the entropy of the Bath region is going to be equal to the entropy of an interval that extends through the ADS spacetime, as shown in this picture. So now this is the entropy of an interval. So we just need to consider the 2-point function of the twist fields, take its derivative, take n goes to 1, and you'll get this answer, which is a log of a cosh of u at late times. The cosh becomes an exponential, and therefore you will get this linear growth as promised. There are also some constant factors which depend on the cutoff and so on, but they're constant, and I'm going to ignore those. And the thing to stress here is that this is true for all time. Okay? For all, it just keeps growing for all time forever. Let me pause here for a few seconds for questions.
Well, there are no current questions, but maybe someone wants to ask now.
Can I ask a question?
Of course.
Yes. So I was just wondering, why did you have to change over to the entropy of the interval extending through the ADS region if you're using just the twist operators in the CFT to calculate the entropy? Is it not the same calculation?
It's the same calculation, but I just did this just for pedagogy.
Okay, thank you. Sorry, and these are inserted in the Bath region, which is this CFT2, right?
Yeah, it's in, so yes, these points are in the flat space region.
Flat space region, yes.
Yes,
Okay.
but remember that the CFT lives everywhere. So there's a two-dimensional CFT that lives everywhere. In the ADS region, what changes is the background metric of that CFT.
Okay, fine. Yes, true. Thank you.
Yeah.
Okay. There also raised hand from Sunil Saki. Please go ahead.
Can you explain why this entanglement entropy increases from the picture of ingoing and outgoing Hawking quanta?
Sure. So here's the picture. Let's just focus on the two wiggly Hawking quanta that are entangled with one another. Let's compare the interval at t equals 0 or u equals 0 and at this future time u. As you go from this slice to this slice, you notice that this Hawking quanta gets captured. And so this means that the entanglement of this Hawking quanta with its interior partner will now contribute to the entropy of the interval B. Did that answer your question?
Yeah, thank you.
Okay.
Yeah, I don't think there are any more questions.
I'm sorry, can if I can ask one quick question again?
Yes.
Can you go to the last slide again? So the fact that you can call this as the entropy of the Hawking radiation is simply because you have transparent boundary conditions at the eternal, at the boundaries. Because this sort of a calculation you also do in the usual eternal black hole case in, say, ADS3 CFT, when you don't have transparent boundary conditions there. So the Hawking quanta just, I think, go to the boundary and they bounce back. Is that not true?
That is correct. It's important to have the flat space region and transparent boundary conditions.
Right. Okay. Thank you.
Yeah. And a comment. Let me make two comments about this spacetime.
Okay. Yeah.
So one is that everything I'm saying right now also applies to the usual flat space Schwarzschild spacetime, the maximally extended Schwarzschild spacetime, the wormhole, in any number of dimensions. What I'm saying here applies to that as well. The other point is that you might have asked me why did I consider this weird time evolution of evolving the intervals up on both sides? That's because the other time evolution, where you take one up and one down, is a symmetry of the problem, because we have a boost symmetry. This space-time and the quantum state has a boost symmetry. Yeah, so I just wanted to make these two comments. Okay. Are there any further questions?
Well, I got a new question in the chat from Eretz Urbach. What's the shape of S B of U for negative and large U?
It's the same, but now just put an absolute value on the U. So if you start at 0, then it starting from t equals 0 and going up, it approaches a linear growth. Start from 0 and go down, it also approaches a linear growth. It grows in both directions. It doesn't go negative, I promise you.
And there's also now a question from Arif Mort. Please unmute yourself.
I've gotten myself confused with something. So you are counting the entropy of the radiation that's coming out, but then that was supposed to be in equilibrium with the black hole from the with the bulk region. So there must be quanta going in too. Where are the contributions of those?
Yeah. So again, let's look at this picture.
Right. So they are going in. So these arrows, and so that is also going to increase the entropy.
Yes, exactly. So the entropy grows because of two things. So if you look at the right movers, it's the capturing of this mode increases the entropy. And now if you look at the left movers, it's the escape of this mode that causes an increase of the entropy. Why? Because at t equals 0, this mode is entangled with this mode, and they're both contained in the region B. Therefore, the entanglement between these two modes does not contribute to the entanglement of the region. But once this mode escapes the region, it's no longer here, say at some later time, it's going to be entangled with the mode which is still in the region. And therefore, the entanglement between these two modes also increases the entropy.
So there's some factor of 2 coming in then somewhere.
Yeah, exactly. There's a factor of 2.
Gotcha. Thanks.
Yeah.
I think we can go ahead.
Very good. Okay, so now why is this a problem? So there are 3 perspectives. So one is that this should imply information loss. Okay? This would follow if you have if you take the Bekenstein-Hawking entropy of the black hole, or the wormhole in this case, to be an upper bound on the von Neumann entropy of the black hole or of the wormhole. I remind you that maybe I'll say more about this later, I'm not sure, but the Bekenstein-Hawking entropy of a black hole can be thought of as, or not can be, but is the thermal entropy of that black hole. And I believe it's a theorem that the thermal entropy or a von Neumann entropy, or rather, the thermal entropy is the maximum amount of von Neumann entropy a system can have with given fixed energy. Okay, so here we have a black hole of some fixed energy, and therefore it has an upper bound on its von Neumann entropy. So we can suppose that that in our calculation that while the entropy of the radiation continues to grow linearly for all time, that maybe that the entropy of the black hole, yes, it might grow, but then it should saturate at the thermal entropy or at the Bekenstein-Hawking entropy. This is sort of the expected scenario if you believe in A, the calculation that we just did, B, that the black hole should have an upper bound on its entropy. Let me stress that I did not show that second point. I did not prove to you yet that the black hole entropy is truly upper bounded by the von Neumann entropy. And so you'll have a behavior that looks like this. And I claim that this implies information loss. To see this, first note that at t equals 0 or at u equals 0, the radiation and the wormhole are in a pure state. Okay? So that's the starting point at u equals 0. At times before this time, which I'm calling t page, or the page time, that's before the point when the entanglement entropy between the radiation and the black hole, it's a time when the entanglement between the radiation and the black hole is equal to the thermal entropy or the Bekenstein-Hawking entropy of the wormhole. Sorry. So before this time, it's consistent to have that entropy of the radiation is equal to the entropy of the wormhole. Okay. The statement is also consistent with the fact that the union of the two, the entropy of the union, is equal to 0. Okay, so that the total system is pure. But for times after the page time, we run into an issue. So after the page time, the entropy of the radiation is going to be greater than the entropy of the wormhole, because the entropy of the radiation just continues to grow while the wormhole is capped off. Assuming this, you can prove using subadditivity that the entropy of the union cannot be equal to 0. In fact, has to be greater than 0. And therefore, the total system must be mixed. So this says that for times prior to the page time, it's sort of consistent to have the total system stay pure. But for times after the page time, it is the combined system has to be mixed. Any questions about this first point?
Currently, I don't see any questions, but if somebody wants to ask, please.
Okay, just interrupt me if you have a question.
I have a question. The Bekenstein-Hawking bound is a function of the radius of the black hole, so it varies on time. And so what happened with that?
Okay, very good. So when you have, in normal black holes that you form by collapse and evaporate away, the Bekenstein-Hawking entropy would be a function of time because it's just given by the area of that black hole. In our case, the area doesn't change. It's an eternal black hole. It's the same area for all time. Not only that, but we have two horizons. And that's why I've written twice times the Bekenstein-Hawking entropy, or twice times the area over 4G Newton. Does that answer your question?
Yes, thank you.
Okay, so this is scenario 1. Now let's talk about scenario 2, which I will call the remnant or the bag of gold problem, which is to say that there is no bound, which seems like the more reasonable thing to say up to from the calculations that we did up to this point. That no, the number of states, the number of internal states of a black hole can be arbitrarily large and can support an ever-increasing von Neumann entropy. Okay, so here we'll have that the entropy of both the radiation and the wormhole grows linearly as a function of time. The entropy of the radiation grows because of all the Hawking quanta, the outgoing Hawking quanta it captures that are entangled with the interior. The entropy of the wormhole grows because of all the entanglement of the interior quanta that are entangled with the outside Hawking radiation. And so this scenario is good in the sense that the entropy of the radiation is always equal to the entropy of the wormhole. And that the state of the combined system, radiation plus wormhole, is just equal to 0. Okay, so the state remains pure for all time. This is good. But this is also bad. It's bad because in a standard quantum system with a finite number of states below any energy, the maximum entropy at given energy, as I said, is precisely the thermal entropy. And therefore, the wormhole, and for the wormhole, that thermal entropy is just a Bekenstein-Hawking entropy. If you recall from Douglas's talk yesterday, he said that, that there's a claim that if you do experiments on a black hole from the outside, you will get result consistent with analyzing a quantum system with a large number of degrees of freedom, but with chaotic dynamics and so on. This seems to be contradictory to that, because it seems that you can entangle an arbitrarily large external system with this black hole of some given total energy. So this is bad for that reason. It seems like it's not behaving as a standard quantum system. Moreover, this would preclude holography. We know that the ADS spacetime with in this case, the ADS spacetime with a wormhole or a black hole cannot be dual to a unitary quantum system living on the boundary, because the unitary quantum system living on the boundary, those that have holographic duals that we know of, are just, as I said, just regular unitary quantum systems. And so they would have their thermal entropy as an upper bound on the entanglement entropy that they can have. On the right-hand side here, I have a picture just to explain this ever-growing entropy. So you have a lot of Hawking quanta inside, whose number can be larger than the Bekenstein-Hawking entropy, that are entangled with Hawking quanta in the bath region. Any questions about this perspective?
There's one question in YouTube was asked a few minutes ago by another Brunker. Why would we expect black hole entropy to rise? Wouldn't it stay fixed since the area is fixed?
Well, I mean, so ultimately, the entropy of the black hole will not increase indefinitely. Yes, it should be capped off by the thermal entropy, by the Bekenstein-Hawking entropy. That's what we want. But that's why I call this sort of a perspective. So far, the calculations that we did, working in the semiclassical approximation and so on, nothing says that the entropy of the black hole caps off. In fact, we see quite the opposite, because if you look at this picture here, we can just see that the wormhole has a lot of Hawking quanta or interior quanta behind the horizon with a large amount of entanglement. So it seems, I mean, any reasonable person would see this and say, oh, this must mean that the wormhole has a large amount of entanglement. And we know that the number of these internal quanta grows linearly in time for all time, and therefore the entropy is just going to keep growing. And so I'm explaining that there's a conflict between what we see and what we expect, and hopefully we'll explain that later.
Wait, somebody mutes me. There was a raised hand from Arif Mort, but now I don't see it. But if you still want to ask a question, please go ahead.
Oh, well, actually, he answered my question in the previous question we were asked, so thank you.
Okay, so that's the second perspective. Now for the last one, which is unitarity, which is to say that the Bekenstein-Hawking entropy does indeed bound the entropy of the wormhole, which is going to be equal to the entropy of the radiation at all stages of the evolution. So not only is the entropy curve of the black hole saturate, but also the entanglement entropy of the radiation. So here I have this picture. This growing dotted line is the answer that we got, the semiclassical calculation that we got. And but we expect this. But in this perspective, we say that both entropies should grow up to this page time and then saturate at the Bekenstein-Hawking entropy. These curves are called the page curves. Okay, so why is this good? Well, it's good because it's consistent with unitarity, consistent with holography, consistent with this expectation that the black hole should behave like an ordinary quantum system. Great, but up to this point, this is just a wish, it's a hope. And that's explained in the bad section. Well, the first point of the badness is that in our calculation, where did our semi-classical calculation go wrong? Sometimes this question is sort of phrased as, what was Hawking's mistake? So up to this point, we essentially just redid Hawking's calculation. And what we will see is that non-perturbative physics is going to be required to realize this picture. Okay, so the bad point number one is that, well, we need to find our mistake. Bad point number two is that this assumption actually generates a firewall paradox. Okay, so this is kind of a bold claim. The eternal black hole. Remember, I said that this setup is just like it's identical. Well, not identical, but it has the same features as the eternal black hole in asymptotically flat space. Okay, like the Schwarzschild black hole. And this would seem to say that even the Schwarzschild wormhole has a firewall paradox. So let me explain the argument. So if we look at times larger than the page time, as we assumed here, that both the entropy of the radiation R and of the black hole must have maxed out. They're equal to the Bekenstein-Hawking entropy. Now let's consider dividing the system. Let's consider what happens when one more Hawking quantum goes from the black hole to the radiation. Okay, so here I have the radiation. Well, let's first look at the two entangled modes. So we have mode B, which joins the early radiation, rad, and B is entangled with its interior partner A. Okay. The contradiction is going to be between these two statements, these 2 points. So point A is the requirement of having vacuum at the horizon requires that the von Neumann entropy of the union of A and B is 0, that A and B are in a pure state, and that there's entanglement between them. I mean, actually, it's more that they're in a specific entangled state, but for now, it's enough to just say that there's entanglement between them. So SA is equal to SB is greater than 0. Good, so that's the first point. The second is that we have unitarity. So unitarity is, again, the statement that we have the page curve, which says that the entropy of R, or the radiation, has maxed out. This means that if you combine B with R, so B now joins R, the radiation of the new collection of radiation, the entropy of the radiation of the entropy of the new collection of the radiation cannot be greater than its initial value, or the value before including B. So S of R must be greater than or equal to S of R plus B. Okay, that's just a consequence of the fact that the entropy is flat. Okay, you might also argue that it actually has to be equal to, but I don't want to make that strong claim. And the claim is that these two points are contradictory. The way to see that is to just apply strong subadditivity to these three systems, A, B, and R. So strong subadditivity is the following statement, that S of A plus B plus S of B plus R is greater than or equal to S of A BR plus S of B. So let's go through this. So if you look at the left-hand side, from point A, the entropy of SA plus S, sorry, the entropy of the union of AB is 0, so we can ignore this. From point B, we know that the entropy of S of B plus R must be less than or equal to S of R. Good. On the right-hand side, because AB is in a pure state, S of, using point A, S of A plus B plus R must be equal to S of R. Okay? That's again, since S of A plus B is equal to 0. So what we have now, maybe I should have written this in a different way, that S of R is greater than or equal to S of R plus S of B. Delete S of R from both sides, and you'll get S of B is less than or equal to 0, conflicting with point A, which is that S of B is greater than 0. Contradiction. Now, now you can sort of try to now select, which of these two assumptions should we drop? We know that they're contradictory. At least we argued in the first AMPS paper that it's more that unitarity should be cherished, and so it is more reasonable to drop assumption A, which is vacuum at the horizon. Therefore, the vacuum is not NT. It is in fact replaced by a firewall. And that's the picture that I have here. So the fact that A and B are entangled is what guarantees the smoothness of the horizon. But now if we say that at the page time, which is where this argument applies, this entanglement has to break, and there's going to be a firewall that gets generated at this horizon. But note that this space-time actually has a lot of symmetry. So you can use the fact that this is sort of reflection symmetric, reflection going from left to right or from future to past. This singularity there must be a singularity not only here, but also here and here and here. Moreover, the boost symmetry tells you that it doesn't just start at this point, but it actually has to be everywhere. So by reflection and boost symmetry, you reach the conclusion that the firewall is actually everywhere along the bifurcate horizon. The entire horizon is on fire, and it seems to say that the wormhole is a lie. And I think this is a great point and a great note to end my second lecture. Thank you.
Okay, let's thank Ahmed for his second lecture. You can unmute yourself and clap. Yeah, there was a question in the chat from Mohammad Numan Matip. Will you explain a bit the wormhole dynamics in this model, meaning the violation of violation of null energy condition and so
on? So there's no, well, let me see. I don't think there's violation of the null energy condition in this case. I know that when a black hole evaporates and actually shrinks, there's a violation, but I don't think there's violation here. In terms of dynamics, again, this wormhole is in thermal equilibrium with radiation coming in from infinity. And so it's just static. There are no dynamics. Well, there are dynamics only if you look at, well, the geometry doesn't change, is what I mean. But if you look at the quantum state on this interval that I was studying, the union of the two intervals in the bath, time evolved forwards in time on both sides. The quantum state of the bath region changes as a function of time. That's why we're getting all of this time dependence and so on. But in terms of the geometry doesn't change as a function of time.
Okay. There were also some questions in the chat about some of the inequalities you wrote, but I think they were already. And okay, there also raised hand from Arif Moht. Please go ahead.
Could you please say about on the right-hand side page, point 2a, you are saying the vacuum at the horizon. I mean, that would be true for an evaporating bulk, because then you have the Unruh state and that's vacuum at the horizon. But here you have thermal equilibrium, so it's more like Hartle-Hawking. So why would you impose that condition at all?
So the Hartle-Hawking state is actually defined by saying that the two horizons are vacuum. And the Unruh state is the analog of the Hartle-Hawking for the case of a black hole that forms from collapse. But really, even in the Hartle-Hawking state in the eternal black hole, you also have vacuum at the horizon.
How would you differentiate between then a horizon that is in thermal equilibrium versus horizon that's just radiating out?
At the 0th order, you'd say that one is changing size, one is getting smaller, and one is not.
In terms of I was asking in terms of entangled pairs.
It's nearly identical. If you look at the if you have an evaporating black hole, so you need to take advantage of this fact that evaporation is slow. It's controlled by G Newton. G Newton is very slow, very small, and so for reasonable timescales, the horizon even of an evaporating black hole can be well approximated by the horizon of an eternal black hole, just locally. And the quantum state that we're talking about is you can think of it as a local statement near the horizon.
There is a question from Eretz Orbach. Why the firewall argument appears only for the third option? What about the bag of gold?
Let me see. Well, for the bag of gold, let's go through all options. In the bag of gold, we don't have any constraint on the quantum state of the radiation, right? So the bag of gold says that the state of the radiation, so we don't have additional constraints. The quantum state of the radiation here is just a Hartle-Hawking state. The thing that we constructed in the first lecture. So you have the right amount, the correct entanglement, or the correct pattern of entanglement across both horizons for all time. Okay, so that's for the bag of gold. Now you can ask, what about for the information loss scenario? Again, the information loss scenario, we weren't that precise about how the wormhole entropy gets capped off. But maybe one shouldn't say too much about this case, because we already know that this case has drastic violations of unitarity anyways. And so these entropy relations that we would be applying to derive the firewall should not be trusted, because we're saying that quantum mechanics breaks. So I guess maybe I don't have a comment about the information loss scenario. I hope that answered the question.
Okay, there is a raised hand from Aranya Bhattacharya. Please unmute yourself.
Yeah, so could you go to the first perspective that you were mentioning, where after page time, you say that the state gets mixed?
This one?
So, yeah. So why do you say that? What is the argument behind saying that is radiation plus wormhole greater than or equal to 0? I missed that.
Okay, yeah, no worries. So here I'm making an assumption. I'm saying that let's trust our semi-classical calculation for the entropy of the radiation. Okay, so that means that the entropy is going to keep growing for all time. But let's assume that the entropy of the wormhole grows for some time, but then it caps out. Okay, so I'm making this assumption. Then if you look at for times greater than the page time, because of the assumption that I just made, the entropy of the radiation is going to be greater than the entropy of the wormhole. That just follows from this picture that I drew. And you can just use this identity of von Neumann entropy called subadditivity, which proves that the entropy of the union of the radiation plus wormhole has to be greater than or equal to 0. So this means that the total system, the radiation, but by definition, if the entropy of the total system, which is radiation and wormhole, is greater than 0, then it must be in a mixed state. Did that answer your question?
Okay. Yeah, but I'm a bit confused about why do you make this particular choice of about the growth of the wormhole? What is the reason behind this particular assumption that the wormhole grows for the time before each time and then it saturates?
Good. It was just, it's really just a guess. Well, I guess because I know the answer. That it's sort of, so naively from the second point here, the wormhole entropy should just keep growing because of the collection of all the internal Hawking quanta that are entangled with the outside. So that's the naive expectation for the entropy of the wormhole. But we also know from other considerations that the wormhole entropy should have, well, rather the wormhole has a thermal entropy, which should behave as an upper bound on the von Neumann entropy of the black hole, if the black hole behaves as a regular quantum system. And so the most natural expectation is that, okay, fine, it's going to grow, but then something should happen, and then it should just saturate at the upper bound that we assumed for the black hole. And so I'm just considering this scenario, which as up to this point is just sort of an assumption of how things should behave.
Okay. Okay, thanks.
Any more questions?
Also one more thing. This is, you sort of expect this from in regular quantum systems, right? So if you have a system in a pure state of some finite number of degrees of freedom, let's say that you couple it to some external system, there's going to be interaction between the two as a function of time, and this quantum system is going to get more and more entangled with the external system that you coupled it to. Then after some time, this is going to reach its maximum, the amount of entanglement entropy. So it's going to grow, and then it's going to reach the maximum given by the thermal entropy of the quantum system. So this behavior really is, at least the behavior of this growth and then saturation is something that you expect from normal quantum systems, from dynamics of normal quantum systems.
There is a question in the chat from Jivan Chandranamburi. Would the page time depend on just the mass of the internal black hole?
Yeah, so, well, not just that. So let's go, so let's go here. The page time is, so let's derive it. The page time is defined as when the von Neumann entropy of the radiation, of the semiclassical calculation of the radiation, is equal to the Bekenstein-Hawking entropy of the black hole. So maybe I can use my blackboard. So we have C over beta times time is equal to the Bekenstein-Hawking entropy, which is the area over 4 G Newton. And so then the page time is just going to be 1 over C times beta area over 14 meter. So it depends on the Bekenstein-Hawking entropy times the temperature. So this is dimensionless. The beta gives you the dimension, and then there's a 1 over C coming from the number of fields. So this is how it depends on the various parameters.
Shouldn't there be 2? Sorry.
Yeah, sure, fine.
Yeah.
Hi, can I ask a question?
Yes.
Sorry. So just going back to the way you calculated the entropy of the Hawking radiation, if you did not have transparent boundary conditions, this is exactly the calculation that you also do in say 3 or in other dimensions to calculate the growth of the wormhole, right? And the reason why you say that this is exactly also equal to the entropy of the Hawking radiation is simply because you have a transparent boundary condition here. Is that not true?
Yeah. So good. So let's look at this picture on the right hand side. Can you guys see my screen?
Yes.
So let's ignore the bath regions. The radiation. So there's going to be radiation entangled across the horizon, but the outgoing ones get reflected and fall back in.
Right.
So you're correct that the volume of this slice grows as a function of time,
right?
But it contains both the Hawking quantum and the thing that is and the other Hawking quantum is entangled with.
Right.
So the entropy of this region doesn't grow in that case. But in this situation with transparent boundary conditions, one member of the pair gets excluded.
Yeah, when you think from the Hawking quantum point of view, yeah. But from the wormhole point of view, just because the slice is increasing, its entropy keeps increasing in exactly the same way. And it saturates because there is a change of saddle after some point of time.
Right? So ultimately, that's what, we're going to talk about something like that later. But I just wanted to stress that just because the volume is increasing doesn't mean that the entropy is increasing. It just so happens to be the case for this example. Because as you said, in the case of reflecting boundary conditions, the volume increases, but the entanglement entropy does not.
No, but I was talking about the entanglement entropy between the two CFTs, not about the Hawking radiation.
So the two CFTs, you mean the boundaries, or do you mean the matter CFT?
No, the boundaries. The ones that live at the boundaries. When you don't have the bath, it's just the usual ADS3 eternal black hole. You have a computation, involving a single interval on the left and the right boundary, and then you calculate the entanglement entropy between them, and that is linearly proportional to time as well. So in the bulk, that corresponds to the increase in the length of the wormhole, just because the slice connecting them through the bulk keeps increasing.
Yeah, you're talking about this calculation of Hartman-Maldacena.
That's correct. Yes.
Yeah, so that it's that's a very similar effect. I agree.
Right. And there you can say why it sort of saturates, because there is a change of saddle in the bulk, and that's why the entropy saturates. From that perspective, it sort of is clear as to why the wormhole entropy increases and then it saturates.
Well, but that's the entropy of some subregion, so it's kind of different. For example, if you do, well, you can the analog of what I'm saying here, but well, if you do the Hartman-Maldacena calculation, where instead of an interval of the boundary, you consider the entire boundaries,
right, then
you'll just get 0. Right, so they consider a subregion a union.
That's correct. Yes.
But if you look at the entropy of the union of the two,
right,
then you'll just get 0 for all time for reflecting boundary conditions. But if you have transparent boundary conditions, we're actually going to talk about this next time. if you have transparent boundary conditions and you compute the entropy of the union of left-right for all time, then again, it's going to grow linearly in time for all time because of the buildup of entanglement as shown in this picture. And then we're also going to fix that using some other phase transition.
But if you're using twist operators to do this computation, aren't you choosing an interval already? Because you need some position where you to insert the twist operator at the boundary or in the CFT. So that defines the interval for you, does it not?
So we are considering right now well, the thing that I was just describing was we're computing the entropy of the entire left and the entire right. So there are no twist operators.
But in the calculation for the in Hawking entropy, you do have twist operators that you use to do the calculation, right? So
that's right.
Which you use to show that the entropy increases linearly.
Well, I think this question will be more clear tomorrow.
Okay.
I think we should postpone this to tomorrow when I develop some more technology.
Okay, thank you.
Yeah.
Okay, maybe the last question for today. There is a raised hand from Berdat Trekhavi. Please go ahead.
Okay, so my question is, we started by preparing a state at time 0, which was the Hartle-Hawking state. And then we calculated the entanglement entropy in that particular geometry in later times, and we saw that it grows. But from the CFT point of view, it seems reasonable that as we evolve time, we get a state which is a superposition of different semi-classical geometries. So why do we insist on using the same semi-classical geometry to calculate the entanglement entropy in later times?
Can you expand on why we expect that we should get superpositions of semi-classical geometries?
I mean, at least it's not strange to me if we, in general, when we time evolve a state with a, with a general Hamiltonian, we don't expect it to look similar. So it's not strange that if we get, a superposition of different.
Okay. So the short answer I would give is that so far we were trying to reproduce Hawking's calculation and the information paradox as he found it, which was to work within the approximation of semi-classical physics, where you ignore effects of the type that you just mentioned, that you can get superpositions of geometries, or that quantum gravity is important, and so on. You're just propagating fields on a fixed background, and we are led to these problems. But later we will see that quantum gravitational effects of the sort that you were sort of hinting at they do become important, and not at the level of saying that the geometry that you have this that the picture of the geometry is incorrect, but rather that in a certain calculation of in particular the calculation of the entanglement entropy, you get contributions from different geometries, and hopefully that will make you happy when you see it.
Okay, thank you.
Okay, let's thank Ahmed again. And, as a reminder, you can always you feel free to ask also questions on Slack at any time, and we will reconvene in roughly 1 hour 35 minutes with the second lecture by Douglas Stanford.
All right, thanks, guys.
chi presenta il posto dovrebbe
Okay, hello. Get my screen going. Okay. Looks okay?
It's fine. Well, there are a bit of margins, but I think it almost fits.
Oh, well, okay.
Okay, I think we can start. We're happy to have Douglas Stanford, his second lecture about more on quantum black holes.
Thanks. So, as you might remember, last time we were exploring this relationship between black holes and ordinary quantum systems with many degrees of freedom and strong interactions. And to explore that relationship, our strategy was to try to compute some things about the black hole and see if they looked reasonable from the perspective of a quantum system, interpreting the black hole as an ordinary quantum system. So last time we talked about two things. Talked about the thermal partition function, z of beta. That's trace of, it's interpreted as trace of e to the minus beta h. And the real-time correlator, g of t, for two operators in the thermal state for a black hole and JT gravity. And at first look, the answers that we found looked good. They looked compatible with the claim that a black hole resembles an ordinary quantum system. In particular, the thermodynamics that we get from this partition function looked sort of reasonable. And the 2-point function exponentially decayed in time, representing thermalization of the quantum system. So we were happy to get those answers. But on a closer inspection, we ran into some trouble. And this trouble goes by the name of Maldacena's version of the black hole information problem. So we saw two versions of it. For the case of the 2-point function, the problem was that it decays forever. This exponential decay just continued forever. And that's not consistent with general features of quantum mechanics, that the 2-point function should be a discrete sum of oscillating terms, and discrete sums of oscillating terms can't just decay forever. So we found some problem with some very detailed problem with the function that we got. And there was a similar problem for z of beta that we'll comment on a little bit more later today. Okay, so that's where we were, that's where we got to yesterday. And at one point, one of you made a really good guess. Maybe the problem that we're experiencing arises because we used a classical approximation in order to compute the partition function, and a classical approximation plus a geodesic approximation to compute the correlator, g of t. So I think the guess is that maybe if we add quantum fluctuations to these calculations, so we improve our calculation beyond the classical approximation to include quantum fluctuations, maybe then we'll get answers that are compatible with the black hole being an ordinary quantum system. So it turns out the answer is no, but it was still a really good guess, and we should try to understand it. So normally in quantum gravity, it would be hard to check. So I say here the answer is no, that integrating over quantum fluctuations doesn't solve the problem. But normally in quantum gravity, it would be really hard to check that. And the reason is that we can't just do the full path integral over quantum fluctuations in quantum gravity. It's too hard. It requires the UV completion of the theory. And the calculation would be impractical even if we had in mind a particular UV completion. But JT gravity is simple enough that we can actually do the calculation. And I'll sort of sketch how that calculation is done. So for simplicity, we're going to think about the partition function, z of beta, instead of the 2-point function, g of t. Well, we'll comment on both of them, but we'll spend most of our time talking about the partition function, z of beta. And you remember that the problem for z of beta was defined by saying that we need to integrate over 2-dimensional metrics and dilaton fields that have as a boundary condition a big circle where the dilaton has some particular value. And yesterday what we did was we just found a classical solution compatible with those boundary conditions. It was a part of the hyperbolic disk. And what it would mean to do the full path integral over quantum fluctuations would be to integrate over all metrics that satisfy these boundary conditions. We don't just take the solution to the classical equations, we integrate over all metrics and dilaton profiles. And in principle, the path integral could have contributions from very irregular 2-dimensional geometries and wild configurations of the dilaton phi. But that's the problem that we would like to understand. Okay, so because JT gravity is very simple, it's possible to actually do this integral exactly. And there's basically 2 lucky simplifications, 2 special features of JT gravity that make it really easy to do the calculation. So the first one is the following. If you remember the action of JT gravity, the bulk part of the action was the dilaton phi multiplied by r plus 2, where r is a scalar curvature. And in that expression, the dilaton appears linearly in the action. It only appears linearly. And when you integrate over a field that appears only linearly in the action, it imposes a delta function constraint. So let's forget about functional integrals for a second and just remember ordinary 1-dimensional integrals. So this expression here, integral dx of e to the ixy, is an integral representation of the delta function, delta of y. And you see that in the exponential here, the x parameter appears linearly.
I have a question. Can I ask a question?
Yes.
No, so can I ask you, if you're doing a path integral, I mean, I would have started with all possible relevant interactions, right? I mean, for example, why don't I add delta phi square term?
Okay.
In a quantum theory, I mean, in a classical theory, if you want to construct a model, that's fine, is it? But if you're going to integrate, then I would have thought that I would start with the all renormalizable terms, including, I mean, if you're adding, for example, term which is linear in phi, why don't I add some potential of phi square?
Okay.
Or grad phi square, grad phi square.
You could add, so you could add more terms. And so there's a few possible different answers I could give. One is that it does make sense to pick just one of those models. So at some point you have to define exactly what model you're going to do the path integral in. And that model would be one with particular couplings for all the different terms you can have in the Lagrangian. And so here we're making one particular choice, and it's sort of a simple choice where we just have this term linear in phi. And then it makes sense to actually do the path integral with that specific choice. But you might object that it's not very natural to pick. And that's true. It's a special model, but it's not quite as bad as you might imagine. So for example, if you do add a potential, then you get a more general function of phi to the action instead of just the linear term. It turns out that you actually get similar results. And in particular, this has been worked out recently in papers by Maxfield and Toriachi and by Witten. And you find something similar. The quantum fluctuations don't fix the problem. If you add a grad
phi squared.
Grad phi squared is actually can be removed by a field redefinition. So that doesn't change the model. So the general two-derivative dilaton gravity theory is similar to this case.
And also the cosmological constant, the normal cosmological constant is set to 0.
Yeah, that's right. But
I mean, if I was thinking of Liouville gravity, for example, I would have added all these terms. And
well, you would add all those terms, but you would make some specific choice.
Okay.
And we could talk about different choices. And
okay.
Yeah, we don't know. You don't know how to do the path integral for a completely general action, but you do know how to do it for a fairly well, a reasonably wide class of similar actions. So two derivative dilaton gravity theories, and the story I'm telling for JT gravity is actually similar to that case. But at least for first take at it, it's nice to use just this linear and phi term, because then this argument is a little bit simpler. Okay, so we went over this one-dimensional integral case where the integral over this x parameter imposes a delta function in y, and the path integral over the dilaton in JT gravity is similar to that. It's like a functional integral version of this statement. So we integrate over the field phi, and the JT gravity action has this term r+2 times phi. And you can think about that as a copy of this integral here at every point in space. So at every point in space, we get some delta function. And the answer for the path integral looks like a product over all points in space of delta function of r+2. So that imposes that the curvature, the scalar curvature, should be equal to -2 everywhere in space. And in 2 dimensions, imposing that the scalar curvature should be -2 is a very strong constraint. It actually rigidly fixes the space to a piece of hyperbolic space. Okay, so what that means is that after we do the integral over the dilaton, the path integral reduces to an integral over metrics with r equals -2. In other words, pieces of hyperbolic space. So I've drawn here that hyperbolic disk again. And yesterday we considered the configuration of the boundary, which was just a circle. That was the classical solution. But if we want to do the full path integral, all we have to do is we have to integrate over different wiggly shapes for this red boundary. Those will all be spaces with curvature equals -2. So we conclude that this intimidating looking path integral over metrics and over dilaton phi reduces to just an integral over these boundaries. So it's a one-dimensional path integral, not a two-dimensional path integral. Okay. So how do you actually do the integral over the wiggly boundary? So one way to do it is to parameterize that red curve. And it's kind of a funny parameterization the first time you think about it, but it's perfectly legal. What you can do is parameterize it by giving the angle theta, the angular coordinate in the hyperbolic disk, giving theta as a function of tau, where tau measures the proper length along this red curve. So we have a coordinate which measures proper length along the red curve, and we're specifying the red curve by giving the angular location in the hyperbolic plane, so the angle in the polar coordinates, as a function of that tau. And that data uniquely determines the location of this red curve up to isometries of the hyperbolic plane. So what we would like to do is work out the action in terms of the variable theta of tau. And yesterday, if you remember, we computed the action, the bulk part of the action vanished, and all we needed to take care of was the boundary term, the extrinsic curvature piece. And the reason for using this parameterization theta of tau is that it's easy to compute the extrinsic curvature. For big red circles, or big red curves close to the boundary of hyperbolic space, the extrinsic curvature is 1 plus the epsilon squared we discussed yesterday times a simple function of theta of tau, the Schwarzian derivative of tangent of theta over 2. So the Schwarzian derivative is this expression here.
There's a couple of questions.
Okay, great.
So yeah, first is from Christian Copetti. Is it obvious that one should use such boundary conditions, that is integrating over boundary geometries? Usually in QFT, we fix the boundary values of the fields to specify the wave functions.
Yeah, so it's right. So here we are fixing the boundary conditions that we're fixing, or we're fixing the length of this red curve. So and we're also fixing the value of the dilaton, but that doesn't determine the shape. So forget about the dilaton for a moment. We're doing some kind of a two-dimensional geometry problem where we're supposed to fix some property of the boundary. And we're supposed to fix a coordinate invariant property of the boundary. The only coordinate invariant property of a one-dimensional manifold like this is its length. So we can fix the length of the red curve, but we can't fix its shape. So it really only makes sense to fix the length like this and integrate over wiggly shapes.
There was a question from Bruno Carnieri da Cunha. What if the curve has self-intersection that is not Jordan?
So good. This is this is something that's a little bit subtle, but if the in principle we should integrate over red curves here that are the boundary of a disk-like domain. And those will be simple curves, so non-self-intersecting curves. So the path integral over wiggly red curves here should be restricted to be over non-self-intersecting curves. So something like what I've drawn here.
And another question from Himanshu. Are we also supposed to add manifolds with different topologies?
That's what we'll discuss in the second half of today's lecture. So you're getting ahead a little, but that's good.
Can you take one more question?
Yeah, sure.
Yeah, there's a raised hand from Arif Mort. Yeah, you can go ahead.
Could you please say that integration over dilaton still gives you a delta function once you have the boundary condition on dilaton? If it's just free over all, it's like e to the ixy integral dx minus infinity to infinity, it's delta function. But if it's some particular values of x, then.
Yeah, good. So the dilaton is constrained to have some particular value at the boundary, but not in the bulk. And here we only used the metric was fixed to have curvature -2 in the bulk. So everywhere away from the boundary, you really are doing an integral over the dilaton from a complete range, a complete contour. So it imposes a delta function everywhere away from the boundary. And so here we're integrating over all metrics that have curvature r equals -2 in the bulk.
Got it. Thanks.
Yeah.
I think we can continue.
Okay, good. So what we're trying to do is compute the action as a function of this red wiggly boundary. And that action depends on the extrinsic curvature. And here we've written a nice formula for the extrinsic curvature in terms of the parameterization theta of tau. Okay, so that means the action, well, okay, so if you take this formula for the extrinsic curvature and plug it into the JT gravity action like we did yesterday, you find the following form for the action. It has the topological piece plus this term integral over tau of this Schwarzian derivative term. And that looks kind of complicated, but if you actually work out the derivatives and integrate one term by parts, you find a very concrete action. integral d tau, we have a theta double prime squared over theta prime squared minus theta prime squared. And theta of tau is just some coordinate that we're supposed to integrate over, some function we're supposed to integrate over with this action. So the whole JT gravity path integral has reduced to just a one-dimensional functional integral with this action here. This is sometimes called the Schwarzian theory. Okay, so there's a second sort of lucky simplification, which is that this integral over theta of tau is a special kind of integral that's one loop exact. And what that means is that you get the exact answer for the whole integral, the whole path integral in this case, by just computing the classical answer, which is what we computed yesterday, and then doing an integral over small fluctuations around the classical action, the classical answer. So just the quadratic action around that point, and you do the Gaussian integral. So concretely, that means that we should substitute in the following form for theta. The classical solution for theta is just a circle. Theta of tau is just linear in tau. And because theta has to go from 0 to 2 pi, as tau goes between 0 and beta, that solution should be 2 pi over beta times tau. So that's the classical solution. And if you plug that into this Schwarzian derivative action, you get the thing that we computed yesterday. But then you're supposed to include a small fluctuation epsilon of tau and do a Gaussian integral over epsilon. So I'm not going to do that action right now, or that calculation right now, although we can discuss it in the tutorial if anybody wants. But the answer is written here. So first look at this piece, the exponential. That's the same answer that we got yesterday in the classical approximation. And the only new thing that we get by doing this exact path integral is we get this factor of 1 over beta to the 3/2, multiplying the classical answer. So this factor here comes from doing a one loop determinant. And unfortunately, including this factor here doesn't help. It doesn't solve the problem that we encountered yesterday. Remember, the problem was that in a quantum mechanical system, z of beta has to be a discrete sum of exponentials. The discrete sum represents the sum over energy eigenvalues of the system. And if you take this function and try to represent it in terms of exponentials of e to the minus beta times some quantity e, then you find that it has the following representation as an integral, not as a sum. So as an integral over energies of some density of states function sinh 2 pi square root of energy times the thermal factor, the Boltzmann factor, e to the minus beta e. So if this had been a sum over energies instead of an integral, then we would have been very happy. We would have been in business. This would have looked like the partition function of a quantum system. But it's an integral over energies and not a sum. And so we have a problem. Okay. So there's a similar thing that happens for the correlator g of t. And in JT gravity, that thing can also be computed exactly. I give some references for that on the Slack channel. Basically, what you have to do is you have to integrate over these wiggly red boundaries again and measure the distance through the bulk between 2 points on the wiggly red boundary. And that's a geometry problem that can be solved. And in that case as well, what you find is you find an integral over energies of the right kind of expression. So g of t on general grounds should be a double sum over energy eigenvalues in the system. The 2-point function of operators O should be a double sum over energy eigenvalues. And what we find from JT gravity is a double integral over energy eigenvalues with the same kind of weighting by the Boltzmann factor and the phase factor from time, but with an integral over energies instead of a sum. So in both cases, we find the problem persists after we include quantum fluctuations. So in the second half of the talk, we're going to come back to this question of the of summing over different topologies. But before we do that, let's take a short break. I feel like 5 minutes yesterday was a little too long, so let's just take a 3-minute break, and then we can discuss questions and then move on. So I'll see you guys in 3 minutes. Okay, so let me see. Maybe I can find. Okay, so let me see if I can answer some of the questions in the chat. So there's a question which is, how is the theta of tau, this parameterization, related to the metric? And so it's nice to use this. In this parameterization here, we have just the ordinary hyperbolic plane. So the metric is completely fixed. And theta of tau just determines the location of the red curve. So it doesn't affect, so there's coordinates in which the theta of tau just means the location of the boundary. It doesn't, the metric inside is always the same, it's always fixed. Okay.
There was a question from John Lemadrid. You want to read it yourself?
Okay, let's see. So, so the question is, we got z of beta by doing a Laplace transformation, and by definition, that means doing an integral. However, there was no way to write a series to represent a discrete Laplace transformation. So we didn't, in principle, we didn't, so we just got some function here. So this this function that we got here doesn't come from a Laplace transformation or anything. It's just some function of beta. This is the answer that we got by doing the path integral. And so then our goal to show that this is compatible with quantum mechanics would be to write this function as a sum, a discrete sum of exponentials, e to the minus beta times e. And well, there's no way of doing that. There's no representation of this function as a discrete sum of exponentials. So I made one argument here that that's the case by saying that this function does have an exact representation as an integral, not as a discrete sum. So if you try to write it as a Laplace transform, then you find that there's a continuous function here, not a sum of delta functions. But you can think about it other ways. So one nice way of seeing why it can't be a discrete sum of delta functions is, suppose you compute z of beta plus it. So you analytically continue in beta. Make beta go to beta plus it, and then you take t very large. Then you'll find that this function here goes to 0 because of the 1 over beta to the 3/2 in front. So it goes to 0 like 1 over t to the 3/2. But a discrete sum of phases, so e to the minus beta e would become e to the minus beta e minus it times e. So as we take time large, we're just changing the phases of the terms in the sum. And a discrete sum of phases like that can't go to 0, as we discussed yesterday. So that's one simple way of proving that this function z of beta does not have a representation as a discrete sum of Boltzmann terms.
There was a question from YouTube. I think this is a follow-up question to the previous question by another person about the self-intersecting curves. So the question is, why does the path integral have to be over boundaries with a given bulk? As I understand, the boundary is an imagined boundary. So why can't it take any shape?
Okay. So the quantum gravity problem that we're doing is over two-dimensional geometries. It's not over, a priori, it's not over curves. We're doing some integral over two-dimensional geometries. And at the moment, we're restricting ourselves to the integral over geometries with the topology of a disk. So we'll discuss other topologies in a moment, but at the moment, we're just doing the integral over topologies, geometries with the topology of a disk. And the boundary of a topological disk will be a non-self-intersecting curve. So if you take this red curve here and let it intersect itself in some way, then you'll have trouble, actually for general shape of that curve, you'll have trouble interpreting it in terms of a two-dimensional geometry at all. So there's an interesting math problem, which is to integrate over all wiggly red curves, whether they intersect or don't intersect. That's a perfectly fine math problem, and it's an interesting one to study. But it's not related to two-dimensional gravity. The version that's related to two-dimensional gravity involves boundaries of a two-dimensional topological disk, and that's a non-self-intersecting curve. By the way, there's a, it's kind of interesting that the self-intersecting constraint doesn't actually matter in the limit where the red curve approaches the mathematical boundary. So in the limit where epsilon goes to 0, the limit that we discussed yesterday, it turns out not to matter whether the curve self-intersects or doesn't self-intersect. So if you like, you can allow it to self-intersect. You get the same answers in this limit epsilon goes to 0.
I don't see any more questions.
Okay, so let's keep going. So far we discussed an approach to solving our problem, which was to integrate over quantum fluctuations. And now we're going to discuss another attempt. So this was also suggested by somebody yesterday and somebody else today, and it's a good suggestion. Maybe we should include other topologies. So the point that was brought up yesterday is related to this, and I want to emphasize it. So the point that was brought up yesterday is that there's no problem here with this function's g of t decaying forever if the spectrum were continuous. And I objected to that. I said, well, okay, if the spectrum were continuous, then the entropy would be infinite. And we found something finite. But if the entropy somehow were infinite and the spectrum were continuous, then we wouldn't have a problem. It'd be okay if these functions just decayed forever. So let's go back to the computation we did of the entropy. We found the entropy S was equal to S naught plus this thing we computed, 2 pi squared over beta. And notice that this expression here will be infinite if S naught is infinite. S naught hasn't played much of a role so far. It's just this constant that we keep dragging around. But if S naught were somehow taken to infinity, then the entropy would also go to infinity. And then we wouldn't have a problem. So you can think about it as follows. The mistake that we're making, whatever the mistake is that we're making, the reason that we're getting these functions that decay forever, it somehow should be related to the fact that S naught is finite. Because if S naught were infinite, then there wouldn't be a problem. Okay, so let's remember what S naught is, what its role is in this theory. So if you remember, S naught is the term in the action that weights geometries according to their topology. So in the action, it multiplies the Euler characteristic. So the weighting of geometries according to S naught is e to the S naught times the Euler characteristic. And the Euler characteristic chi, a handy formula for it is it's the number of boundaries minus 2 times the number of handles. So the geometry we've been discussing so far, this disk-like topology, has one boundary, it's a circular boundary, and it has no handles. So we have chi equals 1. That means that the geometry we've been discussing so far is weighted by e to the S naught. So that's this case here, a topological disk is weighted by e to the S naught. But if we allowed ourselves to put a handle on the disk, then we would have chi equals 1 minus 2, which is equal to minus 1, and the weighting would be e to the minus S naught. So if S naught is infinite, we only use the disk topology as we've been doing so far. But if S naught is finite, then we should include non-trivial topologies. We should include this handle on a disk and 2 handles on a disk and other things. Okay. So here's basically the punchline of what happens to the correlator. And I gave a reference for this on Slack. We're not going to discuss this case in too much detail. We'll discuss something else. But remember yesterday we're computing this correlator, g of t, and we computed it first by working in Euclidean time. We computed g of minus I tau. And then we got the answer by analytic continuation. And yesterday we computed g of minus I tau by computing the geodesic distance between points on the disk, the boundary of the disk. But if we consider this topology here with a handle, then it's possible to consider the contribution to the 2-point function from a geodesic that passes through the handle. And if you compute that, you find after continuing to real time, tau goes to IT, that the result is no longer decaying in time. So we had this exponential decay from the computation yesterday. And if you include this geometry here with the handle, then you find that the correlator is no longer decaying exponentially. So it's actually not too hard to work that out, work out the answer for that correlation function. But it's a little bit hard. So what we're going to do is study an even simpler case. So instead of considering the 2-point function g of t, let's consider the following quantity, the absolute value squared of the partition function where the argument beta has been continued to beta plus it. We discussed this quantity 2 slides ago in order to prove that the function that we had was not a discrete sum of phases. But we're going to discuss it again now. So this thing is sometimes called the spectral form factor. And you can write it as a product z of beta plus it times z of beta minus it. So let's just write out what that would look like in an ordinary quantum system where we sum over energy eigenvalues. So there's a double sum, one sum for each thermal partition function. And we get the following form: e to the minus beta times the sum of the energies times e to the it times the difference of energies. So as a function of time t, this expression is a sum of phases, sum of oscillating phases. And so it cannot decay to 0 for large t. This is by now a very familiar argument. Okay, so the computation that we did yesterday of the partition function and the improvement with the one loop determinant that we did today gives a function that does go to 0 as t goes to infinity. So let's understand that. So for a first pass through this slide, ignore this wormhole here and ignore this expression. Let's focus on the two topological disks and these two expressions in parentheses. This is the computation that we've done so far. And we're trying to compute z of beta plus it times z of beta minus it. And it's convenient to think about just computing z of beta 1 and z of beta 2, where beta 1 and beta 2 can be complex. Eventually, we'll take beta 1 to be beta plus it and beta 2 to be beta minus it. But let's leave them general for the moment. Then the product of two of these partition functions can have a contribution from a product of two topological disks, where we integrate separately over the wiggly boundaries in the two disks. And the answer for this partition function that we found a few moments ago is shown in parentheses here. We have the classical term from yesterday, and we have the one loop determinant. So we just have two copies of that calculation for the two disks. And if we follow that expression by substituting in these values for beta 1 and beta 2 and taking time t to be large, then we find this expression here, e to the 2 s naught divided by t cubed. So it's going to 0 for large time t. Okay, so that's a problem. But what happens if we include a different topology? So the boundary conditions for z of beta 1 and z of beta 2 is that we should have two circles of lengths proportional to beta 1 and beta 2. And here we arrange those two circles to be in their own separate disks. But another possibility is that those two circles are boundaries of geometry with the topology of a cylinder. So there's a connected geometry connecting the two circles together. And the answer you get for that cylinder is this expression. And I'll explain how you compute it in a little bit. So it's some definite function of beta 1 and beta 2. And if you substitute in these values for beta 1 and beta 2, then you get t over 4 pi times beta. So the first term here is decaying with time, but it's big because it's proportional to e to the 2 s naught. We should think of s naught as being a large number. So the first term is big, but it's decaying in time. That comes from the two disks. The second term is small, but it's not decaying in time. In fact, it's increasing a little bit in time. So it doesn't have an e to the s naught enhancement, but it's increasing a little bit in time. Okay, so let's see if we can make sense of this contribution. Let's try to compare this function to something. So yesterday we saw that the thermodynamics of this black hole that we got from z of beta match with a type of quantum system called the SYK model. So one thing we could do is we could try to compare the answer for z squared that we just computed to what you get for the SYK model. And here I'm just going to plot for you some numerical data. The SYK model is some concrete quantum mechanical system that you can simulate on a computer. And you get the following plot. So I'll explain what the plot is. So first of all, it's a log-log plot where the y-axis is the spectral form factor, which means this z of beta plus it absolute value squared. And the x-axis is the time parameter t. Beta is fixed to some constant in this plot. The red curve it almost doesn't look like a curve. It looks like some kind of thick mess, but it's an erratic red curve. That's the answer for z of beta plus it squared for a particular realization of the SYK model. It's a very complicated function. It's quite erratic. And the black curve, the smoother black curve, is an average for many different realizations of the SYK model. So you can think about that as an average for many different similar but slightly different quantum mechanical systems. You could get a similar black curve by just doing an integral over time to smear out the erratic oscillations in the red curve. But so there's some erratic red curve, and if you average it either over quantum systems or over time a little bit, you can average it and get something smoother, and it looks like what's shown in the black curve. So this is somehow what we should expect to get for the spectral form factor quantity. So this is what the answer would look like in an honest quantum mechanical system. And we're supposed to compare that to what we got in the black hole. So there are three regions of this plot with sort of qualitatively different behavior. They're labeled the slope, where it decays initially, the ramp, where it's growing a little bit, and then the final plateau. And the answer for this plot in the slope and ramp regions actually match quantitatively with what we found in JT gravity from this first term from two disks, and the second term coming from the wormhole. So if you like, this black curve, this in the ramp region is like a quantum mechanical experiment that reveals that the wormhole prediction is correct, that this contribution here is actually visible in the quantum mechanical system. Okay, so you'll notice though that this function here, t over 4 pi beta, well, it has the right kind of slow increase to describe the black curve, but it's not similar to the red curve really at all, this erratic, wildly oscillating red curve. And those erratic, wild oscillations are very typical for what you get in these almost periodic functions, these functions which are a sum of a whole bunch of phases. They decay for a while, and then they exhibit some kind of erratic oscillations for a very long time. So the answer that we got from the wormhole is sort of has something right about it, like it's the right average value, or it would be the right value for an average of SYK models, quantum systems, but it isn't actually the right answer for a given quantum mechanical system. The right answer has to be some very erratic, crazy oscillating curve. So the wormhole does not give the right answer for a quantum system, but it gives something that has something right about it. So that's a little bit vague, but unfortunately, it's the best that I have to offer right now. The basic takeaway from this computation is that including the wormhole topology gives an answer that has something right about it. In particular, it has the right average value, but it isn't the full answer that you would expect in a quantum system. So we've sort of failed again. We still have a problem reconciling the gravity calculations with the expectations of quantum mechanics. So let me just review the steps that we've taken today. So there was a first idea. So yesterday we found this problem with the functions z of beta and g of t, Maldacena's version of the black hole information problem. And today we discussed two ideas of ways to fix the problem. One idea was to include quantum corrections in the disk computation, integrating over these wiggly red curves. And that turned out not to help at all. A second idea was to include non-trivial topologies. And at least for this quantity here, that gives the average of the right answer, but not the actual right answer for a specific quantum system. And there's a little bit more to say about this, but for the moment, that's what we find. So I think basically we've gone through two ideas here, and it seems like new ideas are needed. We need some idea number 3. I'm not going to have time to discuss this in my lectures, in part because I'm not an expert in it, but it seems likely that to get the full answer, this erratic oscillating red curve, the real representation of these functions as the sum of phases, we need to understand the microstates of the black hole better. And I put a reference on Slack, a review article about something called fuzzball geometries. And that's one approach to this. I don't know if it's the right approach or not, but it's an interesting thing and another possible idea for solving this problem. Okay, so so far we sort of discussed the interpretation of this cylinder. In the last few minutes, what I want to do is to discuss the actual computation that we do, that one can do to get this answer that we liked. So the way to form this cylinder geometry is to glue together two slightly simpler geometries called trumpets. So you can think of this cylinder geometry as a double trumpet formed by gluing together two trumpet geometries across a geodesic boundary of some length b. So this trumpet geometry is a geometry which has one big asymptotic boundary with the wiggly red curve out here, a regularized mathematical boundary of hyperbolic space. And the other boundary is just a circle, a geodesic circle of some length b. And we can glue together the full cylinder by taking two of these with the same length b and gluing the two circles together. And then we end up with a geometry that has two of these asymptotic wiggly boundaries. And when we glue the two trumpets together, there's two parameters that we have to integrate over. One parameter is the length of the circle. So to glue the two circles together, you should integrate over the length of the circle. But another parameter is the freedom to rotate one of the trumpets relative to the other before gluing them together. So there's two parameters, b and tau. Well, these are sometimes referred to as length twist coordinates or Fenchel-Nielsen coordinates. And we're supposed to integrate over b and integrate over tau, the product of two of these trumpet geometries. And that gives the answer for the cylinder. So here, z trumpet of beta and b is a path integral over these wiggly boundary at the big end of the trumpet. So z trumpet of beta and b has fixed geodesic circle at one end and a wiggly boundary at the other end. And the computation of z trumpet is sort of similar to the computation that we did for the disk topology already. So you have some classical piece here, which comes from evaluating the extrinsic curvature of just a circular configuration. And then you have a one loop determinant piece, proportional to 1 over beta to the 1/2 instead of 1 over beta to the 3/2. So if you take this function here, this explicit function, and plug it into this integral, do the integral over beta of b and tau, then you get the expression that we had earlier, square root of beta 1 beta 2 over 2 pi times beta 1 plus beta 2. Okay, so let me just, this is my last slide today, so let me just note two things about this cylinder answer. The first thing is that it doesn't depend on S0 at all. The reason for that is because the order characteristic of the cylinder is 0. So if we think of S0 as a large parameter, then computations on the disk are enhanced by e to the S0, but the cylinder is not. So you should think of the cylinder as a very small correction to two disks. It's not enhanced by this large e to the S0 factor. The second feature is that the cylinder geometry is not actually a classical solution to JT gravity. And you can see this from the integrand here. If we take two of these factors, e to the minus b squared over 4 beta, one factor for each of these two trumpets in the integrand, then you'll find the following dependence on b, e to the b squared over 4 times 1 over beta 1 plus 1 over beta 2. And this is not stationary with respective variations in b. So b is an integration variable, And you can see here that the action is not stationary with respect to variations in B, which means that it's not a classical solution. But in this theory, it's simple enough that you can just do the full integral over B. So there's no problem in doing the path integral, even though there's no classical solution. In more complicated theories than JT gravity, this kind of thing would be subtle. But in JT gravity, it's simple enough to just do the full path integral. Okay, so that's all I have for today. Tomorrow we'll start to discuss entropy and the page curve in a simple model of JT gravity.
And thank Douglas. There are a few questions in the chat.
Okay, good. Let's do it.
Okay, so one is from Mohammed Kouemi. What about higher terms, more than one wormhole?
Okay. Yeah, so let me go back. Oops. So let's go back here. So more than one wormhole. I'm not sure exactly what this means, but you could imagine having, yeah, and probably what you mean is you have it's equivalent to adding handles to this cylinder here, connecting the two sides. So we could have some hygenous surface, which has a cylinder here with many holes in it, many handles. And that will give a series of terms that are increasingly suppressed by powers of e to the s naught. So we'll give a series of terms that are smaller and smaller and smaller. And those terms are turn out never to be large, even if the time t is large. So those terms don't become important until sometime here near the plateau, where the whole series breaks down altogether, and you need a different description. So the description with the slope and the ramp, so this initial phase of the curve, is well described by the two disks for the slope and the cylinder for the ramp. And other corrections are very, very small in this region because they're suppressed by powers of e to the minus s naught, and they're not enhanced by powers of t. But then at a later time, that whole description breaks down, and you need to include some other effects. So it's kind of funny that we go through this whole business about how other topologies are important, but to reproduce this curve, really it's just these two topologies that are significant. There's the two disks, and then there's the cylinder.
Okay, the next question is from John Lamadate. Can we think that the wormhole contribution does not go to zero because the time direction is not contractible to a point? I'm not sure if this is correct, but looking at the cartoon, seems that we can not shrink the throw to a point. I'm thinking Mandalcena's paper where the correlator of the BTZ decays to zero, but on thermal ADS3 it does not.
Ah, okay. So that would be okay, so you're right, the time circle is not contractible on this geometry. And you're referring to an important feature that sort of the reason why the g of t function decays exponentially for the black hole geometry is related to the fact that the time circle shrinks. But here we're not computing g of t on this geometry. We're computing the partition function itself. And oh, sorry, maybe the question was about this geometry here. I'm not sure if the question was about the spectral form factor or the g of t.
No, I mean, I don't know too much. I was just thinking like, how can we, for example, get an intuition of the behavior of the form of c squared or of g of t just by trying to understand how is the time direction in the different topologies.
Okay, well, okay, there is actually a simple explanation along the lines that you're suggesting for this factor of t here. So the factor of t arises because of the following. We have two circles, and the length of these circles, the boundary length of these circles, are beta 1 and beta 2.
Yes.
And when t here is very large, then basically the length of the circles is it and minus it. So if t becomes large, then the length is very large. And I mentioned that there's a degree of freedom when we glue these two trumpets together that rotates one of them relative to the other. And so we have to integrate over a u1, the action of a u1 that rotates one side relative to the other. And the volume of that is proportional to the length or the circumference of these circles, which is t. So the reason there's a factor of t in the numerator here is that there's a t's worth of rotations of one side relative to the other that are possible. So, well, that's about the best I can do now, I guess, in terms of explaining that intuitively.
Yeah, yes, that's okay. I was just thinking if we can estimate, for example, different behaviors about what's the property, for example, of the time-leg curves. But yeah, I don't know why t appears on the numerator. I have no idea, I have no clue. But okay.
Well, the reason it appears in the numerator is because of this, the volume of this integration over the relative rotation of the two sides.
Okay, okay. Thank you.
Okay, the next question is from Reiki Van Beest. Why was it started? Why was it we started considering z squared rather than just z?
Okay. So two reasons. One is that this thing is z squared is more similar to the 2-point function g of t. It's a double sum over the energy eigenvalues, quite similar to the 2-point function. So it's a good model for the 2-point function. But the other reason is that if we just consider z, then we don't get any interesting topological contributions like this cylinder. And that's related to the fact that the answer that we get resembles the average of z squared. So suppose I take this plot here and plot z instead of z squared. In the slope region, it would look similar. And in the ramp region, it would also be oscillating in some way, but it would be both positive and negative. And an average of that curve would approach 0. So the black curve, which is an average of the oscillating red curve, would just approach 0 in that case. It would continue to decrease. And you only get this interesting growth of the average when you're averaging something positive. So the average of z squared. If you just average z itself, you get something that continues to decay. And I think in gravity, that's reflected by the fact that you only get this wormhole contribution in the case where you consider z squared, and not if you just consider z.
Okay, the next question is from Thomas Cadina. Well, I guess it's related to one of the previous questions. Why just including the first correction in topologies gives the correct average of the SYK model? What would happen if you include high topologies?
Yeah, so if you can include higher topologies, but orientable surfaces, you get the dots here will have terms in them that are e to the minus. So there'll be another term here that's e to the minus 2s naught. But it will have no time t in the numerator. So even at late times, that term will not look like it's growing large. So this term is important because it's very large at early times because of the e to the 2s naught. And this term is important because it's growing in time. But the further terms in the dots don't have either of those properties. Now, that's true if you consider orientable topologies, but if you consider non-orientable topologies, so where you include cross-caps in this cylinder, you glue some cross-caps into the cylinder, then you can have terms that are growing with time. And those terms actually modify the shape of this curve. And that's relevant for certain variants of the SYK model. So there are actually other types of wormhole contributions with crosscaps in them that can be related to similar plots like this with a slightly different shape. It's not quite linear. It has some correction to the shape. But for the simplest case of the SYK model, the simplest version of this curve, you don't have those effects. And in the simplest JT gravity theory, you don't include the unorientable geometries.
Okay, the next question is from Ignacio Salazar. Is the equivalent to average over realizations to consider an SYK with larger n?
With larger n? Was that the question?
Yeah, that was the question.
Okay. Well, so the SYK model for any value of n would be an ordinary quantum mechanical system. So no matter what the value of n is, if you take a fixed version of the SYK model, so a fixed example, you would expect a curve like this red curve here, even if n is large, no matter what its value is. But on the other hand, if you average, so to get this black curve, this smoother curve, you need to either average over time or average over the couplings, average over the specific couplings in the SYK Hamiltonian.
Okay, so there is also a raised hand from Himanshu. Yeah, maybe you can go ahead and ask.
I was wondering, how am I supposed to think of the trumpet if I was just computing the partition function z? So am I supposed to think of it as something with a half a handle, because like it doesn't have any S naught? So the other characteristic is 0.
Yeah, but it doesn't contribute if you just have one z. So
just a trumpet doesn't contribute to z.
Yeah, no, it doesn't contribute. So the trumpet here is an intermediate computation in a computation of the double trumpet. So in the simplest JT gravity theory, you wouldn't have a contribution to the partition function from just one of these trumpets here. But you could consider a variant of JT gravity where you have some kind of dynamical object in the bulk that the trumpet can end on, like some kind of a brain. And in that case, you could include the contribution of the trumpet. And as you say, it would have order characteristic 0. So it would contribute to order 1 instead of order e to the S naught. So it would be some small correction to the
so it's like half a handle, not like how does it have a characteristic 0?
Oh, well, there's a more general, well, in terms of this counting, we should, so in terms of this counting, you would say that there's 2 boundaries to the trumpet and 1 handle. So chi is equal to 0.
I see. And from SYK model also, like if I compute just z in the SYK model, then it will like match the JT gravity computation with the trumpet, or?
Oh, that's an interesting question.
It would be hard to do because there would be imaginary part of the partition function if you do it for z of beta plus it, but
as far as I know, there's no known SYK effect that is similar to adding just a trumpet with some boundary in JT gravity, but there are some sort of related things in the supersymmetric SYK model. It's not quite a trumpet, but you can add something called a Ramonde puncture, which is somewhat similar to a trumpet. Like a limit of a trumpet as the B parameter goes to 0, and with some Ramonde spin structure. There's another kind of thing that you can add in the different invariants of the SYK model, where you have a cross cap. So this trumpet ends in a cross cap geometry. I don't know where the trumpet has gone. And those make some important effects for some purposes, but I don't know of a case where you would just include the trumpet itself with some fixed value of B, but it's an interesting question, and I'm not sure.
Okay, thanks.
Maybe you can also take a question from YouTube. There was a question from Nanda Brockner. Do you hope to reproduce the erratic behavior? Maybe gravity is the result of the averaging. As evidence, the SYK model isn't conformal for a single realization, but only after averaging. So perhaps the erratic behavior is a bug of the SYT model and not necessarily a feature you would like to reproduce?
Yeah, this is so. This is possible. So, if you study JT gravity in a little more detail and study many different topologies, you find that the whole sum over all topologies is precisely equivalent to a particular kind of average over quantum systems, an average called a matrix integral. So in this very special case, what you suggested is right, that the gravity theory is describing an average of quantum systems. But there are many cases where that should not be true. So we expect to have a holographic dual to specific theories that are not averages. And so it's expected that a bulk theory, including gravity, can also reproduce the erratic red curve and not just the smooth black curve. The problem is that we don't know how. We don't know where this erratic red curve comes from. And this is an open problem.
Okay, there are actually quite a few more questions, but I think we are kind of short. We're already like 10 minutes over time, and in 5 minutes we have to start the next the tutorial. So I propose that we postpone. Yeah, you can ask. You'll have a chance to ask questions in tutorials and on Slack. But yeah, let us thank Douglas again.
Okay, thanks everyone, and thank you for the questions.
Okay, now, yeah, yes, just let me make a quick announcement. So you should have all received emails about how this the next tutorial session will be organized. So there will be 2 groups, and you should receive the mail in which group you are. If you're in group A, you are